Hello, my dear students. Welcome to IMS GATE Academy. Yesterday we started the first session of digital circuit subject. So those who not couldn't attended yesterday's session, so all of you please watch this session. Please watch the previous session in your free time. Okay. So in the last class we have discussed the questions related to the first two chapters. Those are number systems and codes, and then Boolean algebra and K-maps. So regarding first chapter, we have discussed the number system conversions regarding base or radix, and then data representation like sign magnitude form, ones complement form, twos complement form, etc. And then we have discussed the binary to gray code, gray to binary code conversion. Okay. And then regarding Boolean algebra, we have discussed regarding basic rules and laws of Boolean algebra. With the help of that, how to do the simplification of the Boolean function and the representation of Boolean functions like sigma m form or pi capital M, SOP, POS, etc. And then with the help of K-maps also, we have done the simplification of Boolean functions, right? And we have discussed regarding prime implicants, essential prime implicants, and redundant prime implicant. And regarding first two chapters, we have covered good number of questions, and I hope all of you learned a great from these two chapters. All of you learned the concepts which we have discussed in the last class, and the number of questions we have solved good number of questions, and based on the possibility we have discussed the number of methods also, right? So in this particular session we are going to discuss the questions related to the other two chapters, the next two chapters, that is chapter 3 logic gates implementation, and then chapter 4 combinational circuits. Yeah, very good evening Saptak, very good evening. So all of you kindly share this video link with all of your friends so that they also will get benefited by attending this session in live, right? So all of you kindly share this video link quickly. And regarding these three chapters, we'll discuss in the next session, that is on tomorrow. Yeah, good evening Sauvik Paul. Very good evening one and all. So in this particular session, first we are going to start with the logic gates implementation. So in this particular chapter, we'll discuss the questions related to the circuits based on the logic gates. Here you will be having one particular circuit. Okay, you have to find out the output expression. They will give some circuit based on the logic gates. You have to find the output expression. Okay, and then sometimes they will give a specified output. Output can be either 1 or 0. According, in order to get the specified output, what are the combination of zeros and ones possible, they may ask, or they may give the choices. You have to choose the correct option regarding the input combination, etc. Yes, very good evening Pratik. And then we'll discuss regarding logic gates minimization. Here we'll discuss regarding minimum number of NAND gates and then minimum number of NOR gates. So these are the, we will discuss the questions based on these concepts. So all of you please respond. How many of you are eagerly waiting to see the first question? All of you please respond. Yes, very good, very good. So this is the first question. This question is MSQ. That means either one option or more than one option can be correct. Okay. Yes, very good, very good. So here they have given one circuit diagram based on NAND gates and then NOR gate, and they have given 4 choices. Option A, option B is correspond to dual, and option C, option D regarding complement of the output. Okay. All of you try this question. Yeah, very good evening, Vipin. Yeah, thank you. So all of you try this question. Here they have given one logic circuit diagram, but if you look at the choices, these choices regarding what? The concepts related to second chapter, right? So that's why the first two chapters are very important. Okay, if you, in order to solve the questions related to third chapter or fourth chapter or fifth chapter like that. Okay, so it is very, very important. Once if you are strong on the basics, whatever may be the level of the question, you can attempt. Okay, all of you recall the concepts which we have discussed in the last class and apply here. Yes, very good Kundan, very good Saptak. Yes, very good. Others also please try. Still we are having time. So all of you kindly try, and what is the answer you are getting, please share in the chat. Yes, very good Kundan, Saptak, Savikpal. Yes, very good. All of you got the correct answer. See here they have given two NAND gates and then NOR gate. Okay, so here inputs are A and B. So that means you will get output as AB bar, and here the inputs are BC. So output you will get BC bar. Okay, now here you are having a two input NOR gate. Okay, so if you are having x1, x2 are the inputs, if x1, x2 are the inputs, say for example, then NOR gate output will be x1 plus x2 whole bar. Okay, so by using De Morgan's law, you will get x1 bar into x2 bar. Okay, so for the timing I have assumed one input of NOR gate is x1, other input of NOR gate is x2. Okay, so here x1 bar, x2 bar, and here if you observe, both x1 and x2 are already in complement form. Once again, if you are performing complement, 2 times complement means you will get normal function, right? So directly I am writing here Z equal to AB into BC. I am writing directly. See here you are having x1 bar, x2 bar. Here we got x1 as AB bar. So that means complement of x1 is nothing but AB. Similarly, complement of x2 is nothing but BC. So you have to multiply all the terms. Okay, here A you can write as it is, B into B is nothing but B, and then C. So you are getting simply one logical unterm ABC. Simply you are getting a logical unterm ABC. So this is nothing but min-term M7, small m7. See here, if you observe this overall circuit, it is a function of 3 variables ABC, and after doing the simplification, you are getting one product term or logical unterm in which the number of literals equal to 3. Here the number of literals equal to 3 and it is equal to the number of given variables. So we will call that particular product term as min-term, right? So here we are getting M7. Okay, and here option C, option D, they have asked regarding complement. Okay, now if you apply complement to this function, I am considering this one, ABC whole bar. By using De Morgan's law, you will get A bar plus B bar plus C bar. Okay, A bar plus B bar plus C bar, so which is nothing but M7. Or directly you can write complement of min-term is nothing but max term. So that means option D is correct. See, directly also you can write complement of min-term M7 bar is equal to M7. Okay, or just if you perform complement of this, from there also you will get like this, A bar plus B bar plus C bar, which is nothing but capital M7. Okay, so obviously option C is wrong. Option C is wrong. See, here generally students will do the mistake here. Generally, whenever you're having the minterm like ABC, here the values of A, B, C are 1 because all the variables are in the normal form. Okay, suppose if any variable is in complement form, the corresponding variable value will be 0. That is the notation we will follow for the minterm. Exactly opposite you have to consider for the max term. Okay, so here whenever you are having complement, that means the corresponding variable value is 1. Corresponding variable value is 1. When you are substituting here A, B, C values are 1, so the resultant value will get 0, right? So that's why here the answer is M7, it's not M0. Okay, I hope it is clear up to here regarding the complement of overall circuit function. Now let us see regarding the duality. Regarding duality. So here we got Z equal to ABC. Now for this function, if you apply dual, in the last class we have discussed wherever logical AND is there, you have to replace with logical OR. Similarly, vice versa. Okay, but here we are having only one type of operator, logical AND. So when you apply dual, you will get A plus B plus C. A plus B plus C. So you are getting an output function which is having logical OR among 3 variables, right? So if you want to implement by using a logic gate, you require 3 input OR gate. Okay, so that means the dual of the given circuit, overall circuit, if you apply dual, you are getting 3 input OR gate. 3 input OR gate. So that means option B is not correct. So only 2 choices are correct, option A and option D. So the answer for this question is option A, option D. So this is one method. Whatever we have discussed, this is the general method. Okay, now I will discuss one more method. Okay, see here, this is the given circuit they have given. This is the given circuit they have given. Now here you are having NOR gate. Okay, here you are having NOR gate. Just one second. I am redrawing the circuit once again in another form. Can I redraw like this or not? All of you please respond. Whatever the given circuit is there, what I have done, you are having NAND gate, I represented with AND gate and then bubble here. Here also NAND gate, one AND gate, bubble here, and then NOR gate as it is. Yes, good evening Nikhil, good evening. Okay, now you are having a NOR gate with bubbles. Okay, what will be the resulting circuit? Can you guess? You are having NOR gate, but the inputs are bubbles. Say for example, if you are having x1, x2 are the inputs for these 2 input or NOR gate, okay, just before the bubbles you are having the inputs x1, x2, then what you are going to get here? Yes, very good, Saptak, Kundan, Nikhil, yes, very good, all of you are correct. See, for a NOR gate, you know that it is like A plus B whole bar format. Here x1, x2 are the inputs, but you are having bubbles, so that means x1 bar is the one input and x2 bar is another input, but you are passing through a NOR gate. NOR gate means logical OR and then complement. So by using De Morgan's law, you will get x1, x2. So that means this overall logic gate you can replace with simply a 2 input AND gate. A 2 input AND gate. Okay. A 2 input AND gate. So that means whatever the given circuit is there, now you can visualize. Okay, without using pen and paper, you will get the answer. Yes or no? Here you are having simply 2 AND gates, and then here it is nothing but AND gate. Overall circuit is you are having 2 stages AND gates, And here if you observe, AB are the inputs. So that means x1 is nothing but AB, x1 is nothing but AB, and then here BC are the inputs. So that means x2 is nothing but BC, x2 is nothing but BC. Now you are passing these two outputs through a AND gate only. So that means overall output Z is nothing but x1 and x2, which is nothing but, when you multiply these two, directly I am writing ABC. ABC. Yes, very good. Thank you, Nikhil. Yes. See, when you have given circuit systematically, step by step, you can solve. That is the first method. That is the conventional approach. Now, if you are able to visualize like this without using pen and paper, you will get direct answer as ABC. Direct answer as ABC. Okay, right. Now, in the question they have asked regarding duality, regarding complement, that anyway you can calculate. Whatever we have discussed, the same procedure. Okay, regarding duality, you know, regarding complement, you know. Okay, just in order to get the simplified function quickly without using pen and paper, so this is the approach. This is the approach. I hope it is clear for everyone. So if you are having any doubt, you can ask. If it is clear, please mention clear in the chat so that we can proceed for next question. Yes, very good. Okay, now I will show the next question. So this question is also MSQ. That means either one option or more than one option can be correct. Okay, they have given one logic circuit and you have to choose the correct options. Either one option can be correct or more than one option can be correct. And here if you observe two choices they have given in the pi capital M form, and option C they have given one expression, simplified expression, and option D they are asking number of literals present in the minimized function. So that means two choices are related to the minimized function, two choices are related to the standard form. Okay, all of you give a try. Yeah, all of you try. Yeah, Savik Paul, one option is correct among two options you mentioned, among which one option is correct, other option you can cross check once. D is correct. A you can cross check once. Yeah, Savik, you can cross check regarding the complement also. Yes, very good, Vikram Kumar, Shriya Pai, Saptak. Yes, very good, very good. Yes, option B and D are correct. Option B and D are correct. Yes, very good, Savik. Yes, very good. Option B and D are correct. Okay, see here they have given one circuit diagram. Okay, so whatever the inputs are there, so for each and every case, according to the logic gate, just write the equivalent output. Okay, so here A is the input, you are having NOT gate, so the output is A bar. Here for this OR gate, you are having two inputs, one input is A bar, other input is B. So that means output you will get A bar plus B, A bar plus B. Okay, now here you are having XOR gate, inputs are B and C. Inputs are B and C, so that means output you will get B XOR C, B XOR C. Here A bar plus B, here B XOR C. And here you are having a NAND gate, that output for the timing I am labeling as one variable X1. Okay, where X1 is nothing but, you are having these two are the inputs, and here you are having NAND gate, right? So where X1 is nothing but A bar plus B into B XOR C whole bar. A bar plus B into B XOR C whole bar. Okay, when you are having two inputs XY, output of NAND gate is nothing but XY whole bar, XY whole bar, right? Now, here you are having NOR gate, the other input you are having C. One input you are having X1, other input is C. So, F equal to X1 plus C whole bar. X1 plus C whole bar. Okay, by using De Morgan's law, you will get X1 bar into C bar. X1 bar into C bar. See here, X1 you are already having complement version. When you are performing once again complement, you will get normal function. You will get normal function. So that means here X1 is nothing but A bar plus B into B XOR C. I am writing as B bar C plus BC bar. And then here we are already having C bar. I am copying as it is. Okay. Here X1 I already got in the complement form. When you are performing once again complement, you will get the normal function. A bar plus B into B XOR C is nothing but B bar C plus BC bar. Now multiply C bar with these two terms. So this A bar plus B I am copying as it is. F equal to A bar plus B into C bar into C, you will get 0, B into C bar, you will get BC bar, BC bar, okay. Then multiply A bar with this one, B with this one, A bar, B, C bar, A bar, B, C bar, okay. Carefully write wherever complement you are having, okay. B into C bar is nothing but BC bar. From these two, we can take BC bar as common. Then 1 plus anything is 1, logical or operation. 1 plus anything, 1 plus 0 is 1, 1 plus 1 is also 1, because it is a logical or operation, right? So after doing the simplification of the whatever the circuit they have given, for this circuit when you have given 3 inputs A, B, C, after doing the simplification, you are getting the simplified function as B into C bar, B into C bar. So just observe here, in option C they have given B plus C bar, so which is not equivalent to this function B into C bar. Okay, so in this way we have eliminated option C. Option C we have eliminated. Now regarding option D, what they are asking, in the minimized function, just now we got minimized function only, in that how many literals you are having? Regarding that they have given answer as 2. See here, in the last class also we have discussed regarding literal. See, in general you are having the variables always in the normal form A, B, C. Okay, literal is nothing but the variable either in its normal form or in its complement form. Okay, so here B is one literal, C bar is another literal, right? So that means you are having 2 literals. Here you are having 2 literals. So that means the option D is correct. Option D is correct. Number of literals present in the minimized function is 2. Yes, it's correct. Now if you observe option A, option B, you are having pi capital M form. Pi capital M form. See, just now we got one simplified product term as B into C bar. Okay, this one let us try to represent in the standard form, that means sigma M form. Okay, see here you are having one product term, in that product term you are having 2 literals, but in order to get min term, for this particular question, how many literals you should have? All of you please respond. For this particular circuit, if you want to have the min term, in that min term, how many literals you should have? Yes, very good, Kundan, Savik. Yes, we should have 3 literals, right? Because it is a 3 variable function. Okay, in each and every product term, if you are having the number of literals is same as the number of given variables, then that particular product term we will call it as what? Min term. Product term or logical term we will call it as min term, right? So here variable A is missing, so I will multiply this particular product term with 1. After that, this 1 we can write it as A bar plus A. A bar plus A is nothing but 1, right? Into BC bar. Now multiply A bar with this one, A with this one. Okay, so what you are going to get? A bar BC bar plus ABC bar. Okay, so here wherever you are having complement, that means the corresponding variable value is 0. And wherever you are having variable normal form, that means the corresponding variable value is 1. It is very simple. Whatever the values you have considered, when you are substituting here, the overall term you will get 1. Okay, that is the notation we will follow for min terms. Okay, so that means you are getting 2 min terms. Those are sigma m 0, 1, 0 is nothing but 2, 1, 1, 0 is nothing but 6. Sigma m 2, 6 you are having. Okay, but in the choices they haven't given sigma m, but instead of that they have given pi capital M. So here, since the given function is a 3 variable function, regarding 3 variable function, the corresponding decimal equivalent, when you are having 3 inputs, when you write all the inputs in the combination of ones and zeros, you will get the corresponding decimal equivalent range as 0 to 7, 8 combinations, out of which these 2 combinations are min terms. That means for these 2 input combination you are getting output as 1. That means for remaining 6 combinations you will get output as 0, right? So pi capital M 0, 1, 3, 4, 5, 7. Within this range, other than these terms, remaining terms you can write. Okay, so now you look at the option 0, 1, 3, 4, 5, 7. That means option B is correct. So obviously option A is not correct, because both are in the pi capital M form only. Okay, so this is the first method we have discussed regarding this question. This is the conventional approach. Whatever the variables they have given, for each and every stage, whatever the logic gates you are having, accordingly we have written the corresponding logical output function, and then we have simplified with the help of De Morgan's law and other basic laws of Boolean algebra. Okay. Now, if you observe the previous question, this question, actually we are solving the questions related to the third chapter, that is logic gates, but while you are solving these questions, we are using the concepts of second chapter, right? So in the last class, we have discussed regarding duality, regarding complement, right? And regarding simplification of any Boolean function, we have discussed. Whatever the concepts we have discussed regarding literal, everything. So we are applying all those concepts once again in this chapter, right? So in the GATE exam, sometimes they will ask the question related to the specific chapter. Sometimes they may combine the concepts of two different chapters of same subject. Sometimes even they can combine the concepts of two different subjects also, right? So that's why it is very important to learn the basics of each and every subject, so that you can attempt whatever may be the level of the question in the GATE exam, if you are strong on the basics, right? Now, I have solved this question in one method. Okay, now I am going to give one more method. See, just observe here, you are having the circuit diagram and this question is MSQ, and you have to choose among the four choices which one is correct. Okay, right. Just focus only option A, option B. Just focus the first two options. First two options they have given what? Pi capital M. Pi capital M they have given. That is correspond to what? Output function only. Correspond to output function only. Okay. So just observe these two functions regarding 0, regarding 1. Both are same. Regarding 0, 1. In both the functions, same number is there. And here 4, 4, 5, 5. Both are present. Now, the difference where it is coming. Here you are having 2, but they have given 3. Here you are having 6, but here you are having 7. Okay, see what is your observation? For the overall circuit, you will get some output function. Okay, that function when you are representing in pi capital M, obviously you will get one equivalent function. When you are having product of max terms, you will get only one equivalent function, right? But here they have given two choices, pi capital M only, but out of which 4 terms are same, but 2 terms are differed, right? So from this you can start. Say for example, for the timing, we don't know whether option A is correct or option B is correct. Okay, so for the timing, I'm just considering option A is correct. Okay, I'm just assuming. So here, whichever terms are common, you don't need to check those combination. Wherever the terms are different, you just start with that one. Okay, so for the timing, I'm considering max term 2. See here, I'm having 2. 2 is nothing but 0, 1, 0. 0, 1, 0 is the corresponding input combination, right? See, whether you consider min term or max term, whatever the number you're having, regarding that decimal number, you have to convert into binary, simple logic. Okay, here 0, 1, 0 is nothing but 2. For this case, what is the output I'm going to get? Let us analyze. I'm giving input as 0, 1, 0. So 0 bar is what? 1. Next, here already you're having 1. 1 plus anything is 1. So 1 plus 1 is also 1. Next, here inputs are 1 and 0. 1 XOR 0 is 1. So here you're having NAND gate. Both the inputs are 1. Now tell me what is the output you're going to get. NAND gate output. Here you're having 0. I am copying as it. All of you please respond. For a NAND gate, if both the inputs are 1, what is the output you are going to get? Yes, very good. 0. Very good. For AND gate, you will get output as 1. Since you are having complement of 1 is 0. Now you are having NOR gate, both the inputs are zeros. So that means you will get 0 plus 0 whole bar is nothing but 0 bar, which is nothing but 1. See, when you are giving input combination 0, 1, 0, you are getting output as 1. See, when you are having the truth table, at the input side, you will write all the combinations of zeros and ones. Say, for example, here you are having 3 variables. That means you will write 8 combinations of zeros and ones at the input side. Okay, out of which few combinations will produce output as 1. The other combinations will produce output as 0. Right? So now tell me, when you are giving 0, 1, 0 as the input, if you are getting output as 1, now the respective input combination term, whether we will call it as min term or max term. All of you please respond. Whenever you are getting output as 1 for a particular input combination, when you write the corresponding term, here you are having in terms of values, when you write in terms of the variables, what is that particular term we will call it as? Either min term or max term. Yes, very good Kundan. It is the min term. It is the min term. So that means here you are having min term is M2. If you want to write the expression, that will be A bar B C bar. A bar B C bar. Yes, very good Kundan, Saptak, Savik. Yes, for min terms output is 1, for max terms output is 0. Correct, very good. Okay, so but here they have mentioned number 2 in the max term, but here you got min term 2. So that means option A you can eliminate. The moment with the help of 2, when you are able to, here you are getting min term actually, but here since they have mentioned max term, with the help of that you can straight away choose option B. Okay, if you are having any doubt, okay, so let us verify for other combination also. Say for example, here you are having 6. Okay, here you are having 6. For 6 also just verify. 6 is nothing but 110. 6 is nothing but 110. So here when you are giving input as 1, output you will get 0. Here regarding B it is same, regarding C it is same. So 0 plus 1, once again 1, here once again 1, here it is same, here also it is same. So still you are getting the same output 1. So that means here 110 is also min term, it is not the max term. A, B, C bar. A, B, C bar. Okay. Right. So later in your free time, just consider for these two combinations, for 3 and 7, obviously you will get 0. Okay, you can try later. But for the time being, just by looking at the choices, okay, since both the choices are represented in pi capital M, and just with the help of whichever terms are differed, with the help of one combination, I am able to eliminate one option straight away. Obviously, one option is left over, that will be correct. But this question is MSQ, so more than one option can be correct. Okay, now let us focus here regarding option C and option D. So here you got M2 and M6, and regarding this simplification we already discussed earlier. See here, you got the same min terms, right? M2 and M6. And regarding that, here we got the simplified. Okay, or if you want, you can do simplification, you will get the same answer. So just add these two, M2 plus M6. M2 plus M6. See, if you observe carefully, from these two terms, you can take BC bar as common. BC bar as common. Then A bar plus A equal to 1. A bar plus A equal to 1. Okay. So with the help of that, you can eliminate option C because both are not same. And in this minimized function, you are having two literals. So option D is correct. Okay. So this is the second approach. This is the second approach. Just by looking at the choices, from there you will get the clue in order to get the answer quickly. Okay. Is it clear for everyone regarding second method? First method is conventional approach. Systematically we have done. Second method, just by looking at the options, we started. Okay, for one particular input combination. Yes. Now, do you want one more method for this question? Do you want one more method for this question? All of you quickly respond. Yes. Yeah. Now I am going to discuss one more method. Okay. See, this is the circuit diagram they have given, and whatever I have discussed regarding second method, when I look at option A, option B, 0, 1, 0, 1, it is same. 4, 5, 4, 5, it is same in option A, option B. Okay. Now, okay, that is one observation. And one more observation here, if you observe, in option A and option B, okay, in option A and option B, total you are having 6 max terms. Here you are having 6 max terms, here you are having 6 max terms, right? Yes. Yes, Savik. Yeah, I am discussing the shortcut method only. Okay, when you look at option A, option B, they are having 6 max terms. 6 max terms they have given, right? So that means from there you can guess that, okay, for this function you can have minimum 2 minterms. Okay, we don't know really whether we can have 2 or more than 2, but since they have given 2 choices already which are having max terms, and you are having in each function 6 max terms, obviously you are having 2 minterms, right? Okay, now, so this is the indication. So whenever you are focusing minterms, since the number of minterms is less, okay, that is just my wild guess. Okay, if that is so, that means here I want to focus for overall circuit, I want to get the output as 1. I want to get the output as 1. Okay, now just observe, you are having 2 input NOR gate, output is 1. In order to get output is 1, what is the condition for both the inputs? All of you please respond. For a NOR gate, if output is 1, what is the condition for the inputs? Yes, very good. Both the inputs should be 0, right? Both the inputs should be 0. Now just observe here. Here for this particular NOR gate, this input is 0. This input is nothing but what? Your C input. Okay. So here you are having XOR gate. Okay, before that just observe. You are having NAND gate. NAND gate output we should get 0. NAND gate output we should get 0. That means the condition for inputs is what? Both the inputs should be 1. If both the inputs are 1, then only it will produce output as 0. Okay. So here XOR gate output you are getting 1, and you know one of the input is 0. What is the other input value? I hope up to this point it is clear how I got 1 here, and regarding this XOR gate, one input is 0 and you are supposed to get output as 1. What is the other input value? Yes, very good, Saptak. Here 1 XOR 0 is nothing but 1. 1 XOR 0 is nothing but 1. Yes, very good, Naina, very good. 1 XOR 0 is nothing but 1. So here you got B value as 1, okay, and here you are having OR gate, 2 input OR gate, and you are having output as 1. Okay, just now in the previous question we had mentioned that whenever you are having logical OR, 1 plus anything is 1, right? So that means here you are getting 2 possibilities. Say for example, if you are considering here 0, 1 plus 0 is 1, or if you want you can consider 1. Okay, 1 plus 1 is also 1 because it is a logical OR operation. Okay, right. Now if you want to get 0 as the output, for an inverter input is 1. Okay, now if you are considering output of this inverter is 1, that means input should be 0. So that means what is your observation regarding B and C? Regarding B and C, you are having A, B, C. Regarding B and C, the values should remain at 1 and 0, whereas for A, you are having 2 possible values. When you consider A value 1 or when you consider A value 0, irrespective of that, when you are having B value 1, C value 0, for this overall circuit, you will get output as 1. So that means these two are what? Min terms. M6 and M2, these two are the min terms, right? So here my observation point is, since they have given 2 choices, both are in max terms, and since you are having 6 max terms, right? So in order to verify 6 combinations, instead of that, this is giving indication that we may get 2 min terms only. That means you are having only 2 input combination, right? So I started from the output. in order to get 1, I just analyzed stage by stage from output to input like this. In this way, we come to the conclusion that yes, whatever we have guessed, yes, it's correct. So only for these two input combination, we are getting min terms. Obviously, for remaining terms, you will get output as 0. So that means here, if you observe in this pi capital M, you don't have 2, 6. Here you're having 2, 6. So that's why option A is wrong. Obviously, option B is correct. Option B is correct. So regarding option C, option D, we already discussed. This is not correct. This is correct. How many of you like this third method? I haven't done any simplification. I just applied the regarding each and every logic gate. You might have studied, right? Regarding AND gate, regarding NAND gate, regarding all the logic gates. What is the condition in order to get output as 1 or output as 0? But okay, so they won't ask that silly question, okay, for a NAND gate or NOR gate or any logic gate, what is the output you are going to get for a so-and-so combination of input. But the same basics, whatever the functionality of each and every logic gate you are having, for which input combination you will get output as 1, for which input combination you will get output as 0, you are already familiar, right? So that principles only we will use. So in this way, sometimes in the gate exam, they will give the output as 1, okay, and they will ask how many number of input combinations for this particular circuit will produce output as 1, or they may give here output as 0, and they may ask for how many combination of inputs at the regarding input variables which will produce the output as 0, or otherwise they will give the choices among whichever input combination will satisfy in order to produce output as 1 or output as 0, like that. Okay, all of you please respond. How many of you like this third method? Yes, very good, Saptak. Yeah, we'll proceed to the next question. So this is the NIT question. Here they are asking minimum number of 2 input logic gates are of same type. Underline this word. This is very important. Minimum number of 2 input logic gates are of same type required for implementing the Boolean function f of ABC equal to, they have given one function sigma m2345 will be dash, and this is also one more important point they have given in the note. The inputs are available in both normal and complemented forms. So all of you try this question. Read the question carefully and attempt. Yes, very good, Savik, Saptak. Yes. So all of you read this question carefully and try to attempt. all of you try. I'm just drawing K map only. Yeah, whatever you got, it's correct. XOR gate you will get. But here, according to this one, okay, here whenever, see, among all the gates, say for example, if you want to implement any circuit, okay, you are allowed to use only one type of gate. In general, we will use either NAND gates or NOR gates, right? So with the help of NAND and with the help of NOR, you have to answer this question. See, in general, I hope all of you know that the basic gates are AND gate, OR gate and NOT gate, right? Whereas the universal gates are what? NAND gate, NOR gate. So this question is related to, with the help of NAND gates, how many you will get, and with the help of NOR gates, how many you will get, among which is the least one, like that. Yeah, Saptak and Shreya, you are getting 4. Okay, will discuss. Okay. See here, sometimes in the question straightforwardly they will ask what is the minimum number of NAND gates required or what is the minimum number of NOR gates required, like that. But sometimes they will use, instead of directly mentioning that keyword NAND or NOR, but they will give the hint like same type of logic gates are allowed. Okay, so whenever you are getting the question like this, okay, always you have to apply with the help of NAND how many you are getting, with the help of NOR how many you are getting. Okay. So here the Boolean function they have given, f of ABC equal to sigma m 2345, 2345. So 0, 1, 2, 3, 4, 5. So just do the simplification. So you will do the grouping of these two ones and you will do the grouping of these two ones. Regarding this one, you are getting row wise A value is 1, row wise A value is 1, and column wise B value is 0. B value is 0. That means AB bar. And here row wise A value is 0 and column wise B value is 1. That means A bar B. So for this K map, both the groupings are compulsory. Both the groupings are compulsory. So that means both are essential prime implicants. In the last class, we have discussed the difference between prime implicant and essential prime implicant. In this K map, we got two groupings. Okay, and initially I will call these two product terms as prime implicant, and then since these groupings are compulsory, I will call this particular product term as essential prime implicant. Essential prime implicant. Yeah, Savik. See, regarding NAND and NOR, okay, we will call them as universal gates because we can implement any Boolean function with the help of NAND only, or similarly with the help of NOR gates only. Okay, so here the question is with respect to NAND or NOR, or if you want, you can just mention within brackets instead of same type. If you are having any confusion, you can write like NAND or NOR. Okay, with respect to NAND, how many gates you are getting, with respect to NOR, how many gates you are getting. Okay, just to avoid confusion, you can write. Okay, so now you are getting f of ABC equal to AB bar plus A bar B. AB bar plus A bar B. Okay, so this is nothing but A XOR B. This is nothing but A XOR B. Okay, in general, if you are having directly a 2-input XOR gate, with the help of that you will get. Okay, that is a straightforward question, but here I want to discuss with the help of NAND and NOR. So if you want, you can just mention within brackets NAND NOR. Okay, right. So now regarding f of ABC, you are having AB bar plus A bar B. Okay, so whenever you want to check, whenever you want to implement any Boolean function with the help of NAND gates, what you will do? Here you are having the function is in which form? The function is in SOP form. Here you are having product terms which are summed together, okay. So that means it is in SOP form. So whenever you are having SOP form, it is easy to implement with the help of NAND gates. With the help of NAND gates, we can implement any Boolean function if you are having the function represented in SOP form. Okay, how it is, let us see. So here just apply 2 times complement. Okay, you will get the same functionality. For inner complement, apply De Morgan's law. For inner complement, apply De Morgan's law. So first term complement and second term complement, and keep external complement as it is. Now just look at this particular function. How many NAND gates we require and how many NOR gates we require. Here, just to avoid the confusion, you can remove this one. Okay, here the question is related to NAND and NOR. Among those two, which is the minimum? Because if it is straightforward, A XOR B means it is a simple question, but here I want to discuss with the help of NAND and with the help of NOR. So just look at this expression. Here in the question they have mentioned what? Here the inputs are available in both normal form and complemented forms. So that means, see, in general, if they don't mention this one, for any particular circuit, whatever the variables you are having, in general, the normal variables are available. Okay, but wherever you are getting complement, you have to generate with the help of logic gate. Okay, so that means since they have mentioned already complement form is available regarding the variables, you no need to have the any logic gate, right? So here you are having a 2-input NAND gate, here second 2-input NAND gate, and then this is the first one, the second one. You can assume like x1, x2 whole bar. That means we require 3 2-input NAND gates, right? We require 3 2-input NAND gates. We require 3 2-input NAND gates. Okay, suppose if they mention that only the inputs are available in normal form, in that case, what is the answer regarding NAND gates? How many we require? See, my question is, if they not mention that complement form of the variable is available, in that case, you have to generate this B bar also. So that means 3 plus 1, 4. You require 4 2-input NAND gates. Okay, you require 4 2-input NAND gates if only the normal inputs are available. Okay, in general, in the question, if they don't specify regarding the inputs in which form it is available, by default all the inputs are available in normal form. Okay, but whenever you are getting complement form, you require one more additional logic gate. Say for example, if you want B bar, what you have to do? A 2-input NAND gate. For a 2-input NAND gate, you have to connect both the inputs as B so that you will get output as B bar. Okay, right. Now with the help of NAND gates we got the answer is 3. Answer as 3. Now let us see with the help of NOR gates also. With the help of NOR gates also. Yes, Saptak. Yes, Saptak. Yeah, that answer is correct provided if you are having inputs are in normal form. Okay, only normal inputs are available. In that case, you require 4 2-input NAND gates. Correct. Now, whatever the expression here you are having, I am considering once again here f of the output function f of ABC, f of ABC equal to a bar b plus ab bar. This is the function we got. Now, just apply transposition law. Just apply transposition law for this one. So here if you observe a bar plus a, when you do, you will get 1, right? So you should not consider that combination, you consider other variable. A bar plus b bar, here a plus b. A bar plus b bar into a plus b. See, when you multiply a bar into a, 0, a bar into b is nothing but first term, b bar into a is nothing but second term, b bar into b is 0. Yes, both are equivalent, right? So this particular, from this function we have written like this is called transposition law. Transposition law. See, regarding this one, no need to by heart anything. Like here you are having 2 variables, here also 2 variables are there. So just consider any one combination, like say for example a bar plus a, if you are considering overall value you are getting 1, right? So that combination we should not consider. So other combination you can consider a bar plus b bar, here a plus b. Now this function is in POS form. Now this function is in POS form. Okay, so when you're having the function POS form, we can easily implement with the help of NOR gates. Okay, with the help of NOR gates. So here also follow the same approach. Whatever the function you're having, just apply 2 times complement. Just apply 2 times complement. For inner complement, apply De Morgan's law. For inner complement, apply De Morgan's law. Okay, first term complement plus second term complement and keep external complement as it is. External complement as it is. So just observe this expression. How many 2-input NOR gates we require? How many 2-input NOR gates we require? See, in the question they have mentioned that the inputs are available in both normal and complemented forms, right? So that means a bar you no need to generate, b bar you no need to generate, right? Yes, very good Kundan, very good. So here you require a 2-input NOR gate, here you require a 2-input NOR gate. You can assume this is like x1, this is like x2, x1 plus x2 whole bar. Okay, so that means you require 3 2-input NOR gates. We require 3 2-input NOR gates. Okay, so here you got A XOR B, A XOR B. Okay, when both normal inputs, complement inputs are available, when you want to implement with the help of NAND gates, we require 3 only, and even with the help of NOR gates also we require 3 only. Obviously, since both are same, the final answer for this question will be 3 only. Okay, with respect to NAND gates also we got 3, with respect to NOR gates also we got 3. Okay, similarly, say for example, if you are having A XOR B, A XOR B, A XOR B is nothing but A bar B bar plus AB. So all of you try once. For implementing a 2-input XOR gate, how many NAND gates we require? All of you try once. Same. The assumption is same. The inputs are available in both normal form and their complement form. This note you have to consider. Inputs are available in both normal and complement form. See, for this particular case only, we have discussed regarding XOR gate. Just for practice, I am discussing XNOR gate. Kundan, you can cross check once. Others also please try. See, regarding NAND gates, whatever the approach we have discussed, you are having SOP form. After that, we have applied 2 times complement, and then for inner complement, we have used the De Morgan's law, right? After that, you can decide. Similarly, here also, just apply 2 times complement. You will get the same functionality. Now, for inner complement, use De Morgan's law. First term complement and second term complement. First term complement and second term complement, and keep external complement as it is. Here first term complement, second term complement, and keep external complement as it is. Now just look at this expression. In the question, if they have mentioned that the variables in their normal form and their complement forms are available, in that case, you don't need to generate A bar, you don't need to generate B bar, because it is directly available, right? Yeah, Saptak, you can cross check here. See, here it is like x1, x2. When you are having x1, x2 whole bar, you require a 2-input NAND gate. Similarly, for AB bar, you require a 2-input NAND gate. Now you assume this is like y1, this is like y2. For implementing y1, y2 whole bar, you require third NAND gate, right? Yes, very good, Kundan. So we require 3 2-input. We require 3 2-input NAND gates. We require 3 2-input NAND gates for implementing a 2-input XNOR gate. For implementing a 2-input XNOR gate. Now, once again, consider this function just like here. We have considered A XOR B formula, and just we have applied the transposition law. Similarly, you can apply transposition law here. Transposition law here. What you are going to get? A XNOR B equal to, directly I am applying. A bar plus A, if you apply, you will get 1. So that combination you can avoid. So that means A bar plus B into B bar plus A. That is nothing but A plus B bar. A plus B bar. Okay. See, whenever you are having the combination like this, just consider, okay, just by trial. Okay, A bar plus A, you are getting 1. So you have to avoid that combination. You consider other combination, A bar plus B, here A plus B bar. Now, this function is in PYS form. This function is PYS form. Now we can easily implement with the help of NOR gates. So all of you try once. So how many 2-input NOR gates we require? Just calculate. Same assumption. The inputs are available in both normal form and their complement form. Follow the same approach. Just like here we have performed 2 times complement, and for inner complement we have applied the De Morgan's law. After that you can decide how many 2-input NOR gates we require for this particular XNOR gate. Yes, very good Kundan. Others also please reply. Here we are having A bar plus P into A plus B bar. We have to apply 2 times complement. You will get the same functionality. So for inner complement, you just apply De Morgan's law. So the first term complement plus second term complement. And keep external complement as it is. So here A bar, B bar already available. You no need of any logic gate. So you require one NOR gate here, second NOR gate here, and third NOR gate here. So that means here for implementing a 2-input XNOR gate, we require 3 2-input NOR gates. So it is very simple. After understanding this entire thing, Okay, whether they give 2 input XOR gate or 2 input XNOR gate, so the minimum number of NAND gates or minimum number of NOR gates required will be 3 only. For all the 4 cases, the final answer is same. The final answer is same, provided if both normal and their complemented inputs are available. Okay, I hope it is clear, right? But whenever they mention if only the normal inputs are available, or even in the question if they don't specify regarding the input variables, by default only the normal inputs are available. That time, whenever you are getting complement form, you have to generate with the help of other logic gate. Okay, so you can make a note. You can make a note. If inputs are available, if inputs are available, if inputs are available only in the normal form, if inputs are available or input variables, if inputs or input variables are available only in the normal form, only in the normal form, then whatever the 4 cases we have discussed regarding XOR gate, XNOR gate with the help of NAND and NOR, okay, so you will get answer as 3, provided if both inputs are available in normal form and complement form. Now, if the inputs are available only in the normal form, only in the normal form, then here you will get different answers. For the timing, I am just giving the tabular form. So just you can remember this one with the help of one simple logic I will tell. Here regarding 2 input XOR gate, here all the gates are 2 inputs only. Here all the gates are 2 inputs only. Okay, see here I am not given the any derivation here regarding this one when you are having only the inputs are available in normal form, but I am giving one tabular form. Okay, just remember this one logic. If you want any proof regarding this one, okay, I will after this session or okay after this session in the comment I will put, okay, below this link I will put the previous links, okay, which I have discussed earlier in already in the YouTube channel in our company. Okay, so that link I will provide. Okay, you can go through that one in your free time. For the timing, I'm just giving one simple logic. Here you're having XNOR gate. In this XNOR gate, you're having one term NOR. Okay, here also you're having NOR. Okay, the same term, right? So just remember, for this answer is 4. For this answer is 4. Just this is the one simple logic. Here NOR is there, here also NOR is there. Okay, 4. Now, NOR gate dual is what? NOR gate dual is NAND gate. Yes or no? See, NOR gate means what? A plus B whole bar. Say for example, A plus B whole bar is nothing but A bar B bar. If you apply dual to that one, what you will get? A bar B bar dual is what? A bar plus B bar. A bar plus B bar. By using De Morgan's law, this one we can write it as AB whole bar. So that means NAND gate, NOR gate are dual to each other, just like AND gate, OR gate are dual to each other. Okay, right. Now, in the last class we have discussed, yesterday class we have discussed, for a 2 input XOR gate and 2 input XNOR, what are the function we got? Those two are the dual to each other, right? So when you are having 2 input XNOR gate with the help of NOR gates, okay, Now, if you are replacing all the NOR gates with the help of NAND gates, wherever NOR gates are there, if you are replacing with the help of NAND gates, then the dual of XNOR gate, is nothing but XOR gate. This one we already covered in the last class. If you are having any doubt regarding two input case, you can watch that lecture in your free time. Yeah, thank you, Pragya Bharat. Thank you. So, here XNOR gate dual is XOR gate. Okay. So, obviously here, since you are having NOR gates 4, obviously here also answer is 4. All of you please respond. Up to this point, is it clear or not? Up to this point. See, I am not giving any derivation here, just I am giving the hint how to remember when you are having only the inputs in the normal form. For XOR gate, how many NAND gates we require? For XNOR gate, how many NOR gates, how many NAND gates, NOR gates, all the possible cases. Okay. For the timing, I am not giving any derivation regarding this. Now tell me, regarding two input XOR gate, two input XNOR gate, one relation we know, that is a dual. Right? Now, in general, whatever may be the number of input variables you might be having, what is the relation between XOR gate and XNOR gate? In general, what is the relation between XOR gate and XNOR gate? Only for two input case, those are dual to each other also. But for generalized case, XOR gate, XNOR gate are what? Complement each other. Yes or no? Complement each other. So just observe here. Here you have used 4 NOR gates. With the help of 4 NOR gates, you got XNOR gate. Okay. Now this XNOR gate, you got XNOR gate. So just I am drawing the symbol. You got A XNOR B with the help of 4 NOR gates. Now this one I am passing through a 2 input NOR gate, but both the inputs are same. Then this particular NOR gate will behave as what? Complement or NOT gate. Okay. So that means here you will get A XNOR B complement, which is nothing but A XOR B. A XNOR B complement is nothing but A XOR B. So that means, what is your observation? Here we already used 4 and we are using the fifth one here, right? So that means here, if you observe regarding A XOR B, we require 5 NOR gates. Is it clear up to this point? Regarding XNOR gate, we have used 4 NOR gates. That circuit I have considered here, that output I am passing through an inverter, NOR based inverter, then I will get A XOR B. Okay. Apply the same logic. Here I got XOR gate. With the help of NAND gates. Now tell me. If you want to get XNOR, what I have to do? Here I got A XOR B. Now, in order to get XNOR, I have to pass this output through an inverter, which here in this case, I am using NAND based inverter. That means both the inputs I am tying together, then the 2 input NAND gate will behave as NOT gate or inverter, right? So that means here in this case, you will get A XOR B complement, which is nothing but A XNOR B. So that means for getting XNOR gate, here we require 5 NAND gates. See, when the inputs are available only in the normal form, the final answer regarding NAND or NOR, only 2 possible values, either 4 or 5 you will get. Okay, but in the exam, if you are getting any confusion whether answer is 4 or 5, this is the logic. Whatever I have discussed here, that logic, if you remember, you can answer any question related to this model. Okay, these values are applicable only when the inputs are normal form. But in the question, if they specify that if the inputs are available in both normal form and complement form, whenever you are getting output as A XOR B or A XNOR B, you don't need to do any simplification. Directly you can answer the number of NAND gates required or number of NOR gates required is 3. Is it clear? Only for this case only, for all the 4 cases, you will get final answer is 3. Whereas here you may get In one case 4, in another case 5, like that. Okay. Here if you observe regarding XOR gate, with the help of NAND we require 4, with the help of NOR we require 5. Okay, suppose if the question is like this, then in that case what you have to do? Among these two 4 is the least, like that. Similarly here, among these two 4 is the least, like that. Okay, clear? All of you please respond. Yes, I hope it is clear for everyone. So let us proceed to the next question. This is the MCQ. That means only one option will be correct. Among the 4 choices, only one option will be correct. Here they are asking minimum number of NAND gates required for implementing the dual of the Boolean function. For implementing the dual of the Boolean function, f of ABC they have given, which is equal to a plus b into a bar plus c into b plus c. So all of you try. Here the function is a plus b into a bar plus c into b plus c. And you have to apply dual, and then the question is regarding minimum number of 2 input NAND gates. Yes, very good Savik, very good, very good. Others also please try. Yes, very good Saptak, very good. In which method you have done, Savik and Saptak? For simplifying the given function, which method you have followed after applying dual? Okay, right. See here, they have given one Boolean function and they are not asking for this function, but they are asking if you apply dual to this one, for that particular function they are asking minimum number of NAND gates, right? Yes, very good Savik, very good, yes. Okay, just apply dual to this function. Just apply dual to this function. Okay, so for the timing I am assuming the dual of this function as f suffix d, variables are a, b, c. Okay, a plus b, dual is a and b. Here you are having logical and you will get logical. A bar plus c is nothing but a bar and c. Here logical and is there, you will get logical. B plus c is nothing but b and c. B and c. Now you are having three terms. If you want to do the simplification, okay, in the last class we have discussed, that is the consensus law. Okay, with the help of consensus law, you can cross check whether those two conditions are satisfying or not. If it is satisfying, then we can bring these three terms to the two terms, right? So for the timing, if you observe, for the timing I am considering the last term, Here you are having BC, BC. B is present here and C is present here. In this particular term, the missing variable is what? A. That is present here in normal form and in its complement form is present here. It see A can present here, A bar can present here. Okay, and B can present here, C can present here. No problem at all. But whatever the term you have considered, in that term, whatever the variables you are having, exactly it should distribute in other two terms. Okay, and the missing variable should present in one of the term as normal, in other term as in its complement, right? So in that case, what? This is the redundant term. This is the redundant term. So you will get the minimized function as AB plus A bar C. AB plus A bar C. See here the question is what? Minimum number of gates. So that's why before applying 2 times complement for SOP form, so always cross check, is there any possibility to do simplification or not? If not possible, then once again whatever the approach we have discussed, you can proceed. Now you got SOP form. Now the same procedure, just apply 2 times complement, just apply 2 times complement, you will get the same functionality. Apply De Morgan's law for inner complement. Apply De Morgan's law for inner complement. So you will get first term complement. Here logical OR is there, you will get logical AND. Then second term complement, and keep external complement as it is. Keep external complement as it is. In this question, they haven't mentioned regarding the input variables, in which form it is available. By default, the inputs are available in normal form, A, B, C. Okay. Whenever you are getting A bar or B bar or C bar, you have to generate with the help of another logic gate. Okay, right. So here we require one NAND gate. Here for A bar we require one NAND gate. If both the inputs are A, it will produce A bar as the output. Then third NAND gate and then fourth NAND gate. So total we require 4 NAND gates. 4 2-input NAND gates. Total we require 4 2-input NAND gates for implementing the dual of given function. I hope it is clear for everyone. Now the next question. This is the last question regarding logic gates. This is the NIT, so answer will be a number. Here they are asking minimum number of 2-input NAND gates required for implement the Boolean function f of ABC. They have given pi capital M 0 to 3 is dash. Here they have given note, the inputs are available in both normal and their complemented forms. Inputs are available in both normal and complement forms. All of you give a try. What is the answer you are getting? Yeah, so here they have mentioned the inputs are available in both normal and complemented forms. So if you are getting complement form, you don't require any logic gate. Okay. So here they have given the given function is pi capital M 0 to 3. So that means here 0, 1, 2, 3. They have given the max terms notation. That means in the respective positions you have to place the zeros. Okay, you have to place the zeros. Okay, right. See, just tell me, whenever you are having max terms, after doing the simplification, after doing the groupings, and then if you are having pi capital M, in general, after doing the simplification, you will get the simplified function in which form? Yeah, so I will discuss. Okay. So if you are having pi capital M in general, after doing the simplification, you will get the simplified function in which form? POS or SOP? Obviously POS, right? Okay, POS. But if you recall, whenever we are supposed to implement with the help of NAND gates, the given function we have arranged in SOP form, right? SOP form. Yes, very good, Kundan. Okay, but here they have given pi capital M function. If you do the simplification, you will get POS. Okay, if you are having POS, you can easily implement with the help of NOR gates. But here the question is regarding NAND gates. So what you have to do, other than zeros, you have to, in the remaining places, you have to place the ones. If you are considering sigma m form, then you will get, after doing the simplification, you will get SOP form, right? Okay. So now you can do the grouping of these four ones. Okay. For this entire grouping, row wise A value 1, column wise BC values are changing. So that means you will get A. And here you are having two ones, you can do the grouping. Regarding this grouping, row wise A value is changing, but column wise B value is 0, that means B bar, C value is 1, C. Okay. So you are getting two groupings, and from each grouping you are getting one product term. Okay. So in this K map, both the groupings are compulsory, right? So that means the function f of ABC is equal to A plus B bar C. Now this function is in SOP form. Yes or no? Now this function is in SOP form. Now we can easily implement with the help of NAND gates, right? We can easily implement with the help of NAND gates. So follow the same approach. Apply 2 times complement. For inner complement, use De Morgan's law. The first term complement and second term complement, and keep external complement as it is, right? So in the question they have mentioned that the inputs are available in both normal form and complement form, right? So here A bar is there, you don't need of any logic gate. B bar is there, you don't require any logic gate, because they have mentioned that already available, complement form also available, right? So you require here one NAND gate. After that, this is like x1, this is like x2, x2 whole bar. So you require another NAND gate, right? Yes, very good, Saptak, very good. So that means we require two we require two input NAND gates. We require two input NAND gates for implementing the given function. Is it clear for everyone? Savik, is it clear? Here they have mentioned that both normal and complement inputs are available. Okay, if they haven't mentioned that regarding the statement, so that means by default all the input variables are available in normal form only. That time you have to generate A bar with the help of one NAND gate and similarly B bar with the help of one NAND gate. That means NAND based inverter. So you require 1 plus 1 2, 2 plus 2 is 4. In that case answer is 4. Okay. So whenever you are attempting any question related to logic gates, so just read the question carefully. Okay, sometimes in the question they will mention that both the normal and complement inputs are available. Sometimes they will mention only normal inputs are available. Sometimes they won't mention anything regarding input variables, right? So based on the context, you have to answer your final answer carefully. If they mention that complement inputs are available, whenever they mention, you don't require any logic gate for implementing that particular complemented form. Just like when you're having ABC for any particular circuit, ABC are available in normal form. In the same way, if they mention A bar, B bar, C bar also available, you don't require any logic gate. So accordingly, obviously the minimum number of gates required will become less. Okay, so you have to be very careful while you're attempting any question related to the logic gate. Okay, I hope it is clear for everyone. Okay, so with this we have completed the questions related to the third chapter. So here first we have discussed the circuits based on logic gates, and regarding that we have discussed the question related to the output expression, and then we have discussed one question related to the number of combinations of zeros and ones, for which combination of inputs you will get output as 1 or 0 like that. And then regarding logic gates minimization, we have discussed regarding minimum number of NAND gates, regarding minimum number of NOR gates. Okay, right. So regarding NAND gates, always whenever you want to implement with the help of NAND gates, wherever possible you try to arrange the given function SOP so that you can easily implement with the help of NAND gates. Yeah, thank you, Vipin. Whenever you want to implement with the help of NOR gates, try to arrange the given function into PYS form so that you can easily implement. Okay, this is one approach, and one more approach just I will quickly give regarding logic gates. Just recall regarding logic gates. See, the basic gates are what? Say for example A and B AND gate, and then A plus B OR gate. Just 1 second. First I am considering NOT gate A bar, and then AND gate AB, and then OR gate A plus B. See, if you want to implement this function with the help of NAND, what you will do? You will use 2 input NAND gate, but you will make both the inputs are same. Then you will get A bar only. Okay, there is no doubt. Okay, you can easily implement. Regarding AB, here if you want to implement with the help of NAND, by default when you are using single 2 input NAND gate, you are getting AB bar. Now what you have to do? Just now we have implemented NAND based inverter, right? So you have to pass this output through a NAND based inverter like this. Then AB bar whole bar is nothing but AB. Okay, so there is no doubt whenever you want to implement complement form with the help of NAND gate, no doubt. Similarly, whenever you want to implement a 2 input AND gate with the help of NAND gate, there is no doubt. Okay, I will come to this point. Just wait. Similarly, regarding A bar, regarding OR gate A plus B. Yeah, thank you, Shashikant. So regarding A bar, if you are using NOR gate, 2 input NOR gate, A plus A whole bar. Okay, 2 input NOR gate, if both the inputs are same, then you will get output as complement of the input. Okay, with the help of a 2 input NAND gate, you will get A bar. Similarly, with the help of a 2 input NOR gate, you will get inverter. Okay, A bar. Now, regarding OR gate, if you want to produce OR gate, see, if you are using NOR gate, by default you will get complement version. By default, you will get complement version. But now, what you can do? This output, you have to pass through this NOR based inverter so that you will get the normal function A plus B. Up to here, there is no doubt. Okay. Regarding NAND based inverter, regarding NAND based AND gate. Similarly, NOR based inverter, NOR based OR gate. Okay, there is no confusion. Now, if you are having A plus B, that is OR gate, see, whenever you are using a NAND gate, 2-input NAND gate, whenever you are using, what is your observation? By default, you are getting complement version. By default, you are getting complement version. Under the complement, you are having variables among which you are having logical AND operator. Logical AND operator. Okay. But here A plus B, you are having what? Normal function. Normal function. Okay. So, just like here, we have applied 2 times complement. Follow the same approach here also. Follow the same approach here also. But the difference between here and here is, here this particular expression you are directly getting with the help of NAND gate. But here you cannot get, right? So that's why what we are doing, we are applying De Morgan's law for inner complement. A plus B whole bar is nothing but A bar and B bar, and keep external complement as it is. Now A bar we have generated just now with the help of NAND gate. Similarly, B bar you can generate if both the inputs are B. After that, this is like X1, this is like X2. Yes, X1, X2 you can pass through a 2-input NAND gate. Okay, right. Similarly, regarding AB, so just apply 2 times complement, you will get the same function. But whenever you are having a 2-input NOR gate, by default you are getting output in the complement version. Under the complement, among the variables, you are having logical OR operation. Logical OR operation. But here you don't have logical OR operation. Just in order to bring into logical OR operation, we are using De Morgan's law for inner complement. Right. So AB bar is nothing but A bar plus B bar, and keep external complement as it is. Keep external complement as it is. Now, just now we have told A bar you can implement with the help of one NOR based inverter. Similarly, B bar. After that, this is like X1, this is like X2. You can pass through a 2-input NOR gate. X1 plus X2 whole bar, like that. Okay. So you can remember the basic gates, how we have implemented with the help of NAND gates and with the help of NOR gates. With the help of this approach, you can solve any question related to minimum number of NAND gates required or minimum number of NOR gates required for implementing any logic gate or for implementing any logic function also. Okay. Or whatever previously we have told, whatever the questions we have solved, okay, there I have mentioned that whenever you want to implement with the help of NAND gates, the function should be of SOP form. Whenever you want to implement with the help of NOR gates, the function should be of POS form. Wherever possible, you try to arrange so that you can easily implement with the help of respective gates. Okay. So this one, if you want, you can easily observe here. See, when you're having, like generally, this is one product term, you can visualize this one. This is also another product term when you're having multiple variables, right? So this is product term, this is product term. Those two are what? Summed together. So that means this function you can treat it as SOP form. Yes or no? SOP form. So whatever the approach I have told, the same thing, right? Similarly, here you can consider this like one term, this is like another term. Those two terms are logical and together, right? So that means here you are having like POS form. Okay. Here, if you want, you can write A plus 0 like that and B plus 0. Just for easy understanding purpose, I am writing like this. Suppose if you are having multiple variables, this is one sum term, this is one sum term. After that, those two are product together. That means this function is what? In POS form. Okay. So whenever you're having POS form, you can easily implement with the help of NOR gates. I hope it is clear for everyone. So previously I have given with the help of SOP POS approach. Now with the help of logic gates also I have given the approach. So based on your convenience, either you can remember the basic gates, how we have implemented with the help of NAND NOR, or with the help of whatever the questions we have solved. Okay. You can remember any of these two approaches. With the help of any of these two approaches, you can solve any question related to the minimum number of NAND gates or minimum number of NOR gates. All of you, please mention in the chat how many of you got the confidence regarding logic gates. We have discussed all the important concepts. So all of you quickly respond. How many of you got the confidence regarding minimum number of NAND gates and NOR gates? Yes, yes, very good, very good. All of you got the confidence. Okay, so now let us proceed to the next chapter. Next chapter, that is combinational circuits. Combinational circuits. Here we'll discuss the questions based on these concepts. Okay, these are very, very important. So we'll discuss the question based on half adder, half subtractor, then full adder, full subtractor, and then ripple carry adder, and then magnitude comparator, and then decoder, multiplexer. Okay, we will discuss the questions based on these concepts now. Okay, I hope all of you are ready for starting the first question from fourth chapter. So this is the first question from fourth chapter. This is the MCQ question. That means only one option will be correct. Among four choices, only one option will be correct. Here they have given one circuit diagram. You are having circuit 1, circuit 2. Here the inputs are, if the image is not clearly visible, okay, no problem. Just I am writing the variables here. Here variables are WZ inputs. Here XY are the inputs. You are having one circuit here, two outputs are there. Here one circuit is there, two outputs are there. And this direct output we have given to an OR gate, one input. And here this output I have passed through a NOT gate, and then I have connected. And then here final expression they have given X bar into Y bar plus X into Y plus W bar into Z. Okay, this is the final expression they have given. In order to get this expression, you have to identify the circuit 1 is which one, circuit 2 is which one. Regarding that, they have given four choices. Anyway, since you are having choices, you can verify option by option. Whichever option is giving correct answer, that will be the correct. So all of you give a try. Yes, very good, Savik, Saptak. Yes, very good. Others also please try. Yes, just observe here. If you observe all the four choices, you're having in terms of like both are half adders or both are half subtractor, or one is half adder, other one is half subtractor, like that they have given, right? See, just observe whatever the approach we have discussed regarding logic gates, second question, third method. Okay, I have started from the output. I have just verified stage by stage what could be the inputs. Okay, so just observe here the final expression. Okay, see, x bar y bar plus xy you are having. This one we can write it as x exclusion or y. X bar y bar plus xy we can write it as x exclusion or y. After that you are having logic OR and then w bar z. Now if you observe, you're having what? 2 input OR gate. That means you're having 2 inputs here. 2 inputs here. And here you are getting 2 terms only. 2 terms only. Now if you observe, one term you're having among xy. Among xy, here you're having the inputs. Here you're having the inputs. Okay. Right. So from this particular output expression regarding xy, we are having the corresponding term as x exclusion or y. X exclusion or y. Okay. Right. Now you are having NOT gate. NOT gate output is exclusion OR. That means NOT gate input is what? All of you quickly respond. NOT gate output you got XNOR. That means NOT gate input will be what? Yes, very good, Saptak. Complement of XNOR. Okay, so we know that XOR and XNOR are complement each other. For generalized case, whatever the number of input variables, in general XOR and XNOR are complement each other. Okay, right. So here you got X exclusive or Y. So that means just observe here, since you are having choices. Okay, half adder you are having, half subtractor you are having. Okay, right. So here if you consider half adder, then you will get here, this is your sum, this is your sum, this is your carry, x and y. Carry is x and y. Okay, right. So that means here we got this circuit as half adder. Now you are having other term is what? W bar z. That W bar z you can give here as the input, here as the input. Now if you carefully observe, you are having one circuit. Okay, see, if you consider half adder, say for example this one, then what will happen? Regarding sum expression you will get like this XOR, regarding carry expression you will get logical and among normal variables. But here you are having logical and among one variable is normal, other variable is complement. Regarding this one you will get only in the half subtractor, right? So this is your half subtractor. So here you will get, okay, so this is your difference, this is your borrow. So regarding borrow you will get W bar Z. So that means this circuit is half subtractor, this circuit is half adder. So half subtractor and half adder. So you can make this question as MSQ. Actually this is a typo mistake, so you can make the correction. Okay, see here we got half subtractor and half adder. Okay, even if you want, okay, say for example, even if you consider this circuit as half subtractor, then also what you will get? Here in that case you will get difference you will get the same expression, exclusive or only. Whereas regarding borrow you will get X bar Y. Okay, since you require only XOR combination here, okay, you can get with the help of half subtractor and you can get with the help of half adder also, right? Only the difference regarding borrow and carry, there will be the one slight difference. You will get here both the variables are normal, here one variable is complement, right? So just make, this is the typo mistake. Okay, this question is MSQ. So in that case, here in one case we got half subtractor, half adder, option D is correct. And in another case we got both are half subtractors. And then here see, circuit 1 should be mandatory half subtractor. Because here you want complemented version. Okay, complemented version will possible only with the help of half subtractor. So here you are having half adder, so it is not possible. It is not, sorry, not regarding this one. Here first circuit half adder not possible, so you can eliminate. Okay, regarding Option C. Option C also, first circuit you are having half adder, you can eliminate. Is it clear? Regarding circuit 1, it must and should be half subtractor only. Half subtractor only, right? So with the help of that one, you can eliminate option A, option C. Whereas, so here if you observe option B and option C, you are having half subtractor for circuit 1. Okay. Whereas for circuit 2, either you consider half adder or half subtractor, you will get that answer. Okay. So that means both option B and option D are correct for this question. Yeah, thank you, Ankit. Is it clear for everyone? Is it clear for everyone? Both option B and option D, both are correct. Both are correct. How many of you liked this question? How many of you felt this is a very interesting question? All of you quickly respond. Yes, it's clear, right? Very good. Now the next question is NAT, numerical answer type of question. Answer will be number. So this question is based on 4-bit ripple carry adder. 4-bit ripple carry adder or 4-bit parallel binary adder, both are same. Yes, very good, Saptak, Savik. 4-bit ripple carry adder or 4-bit binary adder, both are same, is implemented by using 4 full adders. Okay. And in a full adder, you are having 2 outputs. Okay. You are having sum output and carry output. So regarding both sum delay and carry delays, both are same for a particular full adder. Both are same and equal to 30 nanoseconds they have mentioned. After giving the inputs, in general, if you are considering ideal case, there is no delay. But practical cases, inside any logic gate, you will be having transistors. So after giving the inputs, definitely it will take some time. That is called propagation delay, right? So in this question, they have mentioned sum delay and carry delay, both are same, which is equal to 39 seconds. Okay. Initially up to t equal to 0. Initially up to t equal to 0, A value, A is having 4 bits, it is 0, and similarly B is having 4 bits, all the values are zeros, and carry input is 0. So since all the inputs are zeros, so obviously initial sum output is 0 and initial carry output is also 0, right? So that means for overall 4-bit binary adder, you are having inside 4 full adders. For all of them, all the A inputs, all the B inputs are 0, all the sum outputs, all the carry outputs, all are zeros, all are zeros up to t equal 0. Up to t equal 0 instant, all are zeros. Now, at t equal to 0 instant, what they have done? If the input A is modified as, 1100, that means they haven't modified these 2 bits. They haven't modified those 2 bits. Those 2 bits remain same, 00 only. The other 2 bits, instead of 00, they modified as 11. Now the question is, then the number of possible combinations of B input can be chosen in order to produce the resultant valid output. That means after giving the inputs, in order to get the resultant valid output, okay, by the ripple carry adder, which takes at least 60 nanoseconds is dash. So here initially you are having all the inputs are zeros, all the outputs are zeros up to t equal 0 instant, but from t equal 0 instant onwards you are having this particular input. After giving this input, in order to get the valid output, okay, for which combination of B inputs will take by the ripple carry adder 60 nanosecond minimum. Minimum is 60 nanosecond, either 60 nanosecond or more than that. Like that, how many B combinations we can choose? That is the question. Yeah, Ashish. Yes, I will explain. See here, I hope all of you are very much familiar regarding ripple carry adder. Inside the ripple carry adder, you will be having the full adders, right? Since it is a 4-bit ripple carry adder, you are having 4 full adders. Okay. For each full adder, say for example, at first stage, if you consider A naught, B naught are the inputs, and the respective sum output is S naught, and respect to carry output will be C1. Okay. Similarly, for second full adder, A1, B1 are the inputs, and you will get sum output as S1, carry output as C2, like that. Okay. In that way, you will be having 4 full adders inside. For each full adder, we will give the respective AB inputs, and from each full adder, we will get the respective sum output, and whatever the carry output we will get from one step, we will give as the carry input for next stage, like that. Okay. And here they have mentioned that up to t equal 0 instant, all the inputs are zeros, all the outputs are zeros. But at t equal 0 instant, they have modified the starting 2 bits of A, like 1 1, 0 0 to 1 1 they have modified. The other 2 bits they kept as it is. Now you have to choose regarding B inputs. See, regarding B, earlier you are having zeros, all the inputs are zeros. Now you have to consider the B combinations in such a way that this particular ripple carry adder, after giving the B input, A input, okay, minimum it should take 16 nanoseconds. So like that, how many B combinations you will get? That is the question. Is it clear, Ashish? Regarding the question, I will explain. Okay, regarding the solution, is it clear regarding the question what they have asked? Yes. Yeah, this is the typical question. Okay, so I will explain here. Yeah, Savik, 3 is not correct. Okay, we'll see. You might have chosen only few combinations. See here, A input they have fixed to 1100. A input they have fixed to 1100. Yes, very good, Saptak. Very good. Very good. A input they have fixed to 1100. Now they are asking regarding B inputs. Regarding B input, since you are having 4 bits, regarding B input, since you are having 4 bits, in general you will get 16 combinations. Regarding B inputs, you will be having 16 combinations. Now let us consider all the 16 combinations one by one regarding B, whereas for A, this value remains same. Okay, and we'll see for which combinations you are getting output as. That means in order to get the valid output, it is taking 16 nanoseconds. Let us see. Okay, so here I have considered A input same only 1100. Regarding B input, I have considered here 4 combination: 0, 4 zeros, 0001, 0010, 0011, like that. Okay, in the next slides I have considered other 12 combinations. Okay, I have considered all the 16 combinations. We'll see one by one. Okay, right, just perform the addition. I hope all of you are familiar regarding addition of 2 numbers. So that's why I'm directly writing. So now just observe. Here for according to the given question, up to t equal to 0. Sorry. Okay, I will write once again, no issue. Okay, regarding A input, you are having 1100. Regarding B input, we have considered 4 combinations. Now, here if you observe, according to the given question, up to t equal to 0, all the outputs are zeros. Okay. But here if you observe, when you have given this particular input, okay, now what you are getting? Here this particular sum bit is 1, here sum bit is 1. Similarly here, these 3 sum bits are 1. Here these 3 sum bits are 1. Here all the sum bits are 1. Okay. For each full adder, if you observe here, since there is no carry input, each full adder will take same amount of time for producing the sum delay. Yes or no? If you are having 4 stages, since carry input is 0, since there is no carry input at any stage, obviously each and every stage full adder will produce the sum bit at the same time. Regarding sum bit, they have mentioned in the question the sum delay as 30 nanoseconds. So that means here for all these 4 combinations, the delay is 30 nanoseconds only. All of you please respond up to this point. Is it clear or not? Yes, it's clear, right? Very good. Now let us see the other combinations one by one. So here you will get 0, 0. 1 plus 1 is 2, sum is 0, carry is 1. Here once again sum is 0, carry is 1. Okay. 1, 0, 1 plus 1 is 2, sum is 0, carry is 1, sum is 0, carry is 1. Here 0, 1, 1 plus 1, sum is 0, carry is 1. Once again sum is 0, carry is 1. Now here you are having 1, 1, 1 plus 1, sum is 0, carry is 1. Once again sum is 0, carry is 1. Now just observe. See here you are getting the carry output by the third stage full adder. See here you will be having third stage full adder. That particular full adder is producing carry output as 1 at what instant? At 30 nanoseconds. At 30 nanoseconds, this carry output is 1. Now this particular fourth stage full adder is also producing carry as 1. But this one you are getting at 30 nanosecond. That means this particular delay we have to consider, right? In general, if there is no carry input for this particular full adder, in order to produce the carry output, it requires 30 nanosecond. But since this particular one you are getting at 30 nanosecond, we have to add this delay here. Then 30 plus 30, which is nothing but 60 nanoseconds. Is it clear? Just for easy understanding, I am just drawing the time scale. Say for example, up to t equals 0 instant. Okay. For this full adder, there is no carry input. Here also there is no carry input. Here also there is no carry input. Okay. Now the third stage full adder is producing 1 at 30 nanosecond. At 30 nanosecond, the third stage full adder is producing the carry output. Now, in order to get the valid output, that means in order to get this particular carry output as 1, this particular full adder has to wait for this carry or not. All of you quickly respond. This particular full adder, in order to produce this carry output as 1, whether this particular full adder has to wait for this carry input or not. Yes, it has to wait. It has to wait. Say for example, if it not waited, then what will happen? It will assume that initial carry is 0. Because of that, here the carry output will be 0. But the question is what? In order to get the valid output, means the moment if this full adder is producing carry output as 1, then this particular full adder has to consider that carry. Since this carry is coming at 30 nanosecond. Now after this, you are having a full adder, you are having ABC inputs. In order to produce the carry, obviously that particular full adder actually will take 30 nanosecond only. But since this particular carry input as 1, you are getting at 30 nanosecond. From here you have to consider other 30 nanosecond. So that means it will be 60 nanosecond. Okay. The same case you can observe here also. Here third stage carry output is 1, fourth stage carry output is 1. So that means same 60 nanosecond. Similarly here also, third stage full adder is producing carry output is 1, fourth stage also. Similarly here also, here also. So that means these 4 combinations are producing these 4 combinations in order to get the valid output. Okay, the ripple carry adder actually taking 60 nanosecond, right? So here we got 4 combinations. For these 4 combinations, the ripple carry adder is taking 60 nanosecond after you are giving the input like this. Okay, say for example, A input you modified like this, B input if you are giving like this. In order to get the valid output, it requires 60 nanoseconds. Similarly for all these combinations. Okay, is it clear, Ashish Sharma? Up to here it is clear, Ashish? Okay, now let us proceed further. I hope it is clear, Ashish. Yes. Now let us proceed further. 1 plus 1, sum is 0, carry is 1. 1 plus 1, sum is 0, carry is 1. 1 plus 1, sum is 0, carry is 1. 1 plus 1, sum is 0, carry is 1. Now here if you observe, there is no carry input at any stage. There is no carry input at any stage. Okay, so that means here you are having some delay, and here actually you are getting the carry output only at the last stage. Carry output you are getting only at the last stage. And regarding sum, okay, you are getting in few cases single one, or in few cases 2 ones like that. Okay, and here you are getting 3 ones. But anyway, since you are not having any carry input, each full adder takes the same amount of time for the sum delay, sum bit. Okay, but in this question they have mentioned that the sum delay and carry delay both are same, right? See, just observe here, you are getting sum delay, sum bit as 1, so you have to consider sum delay. Okay, here you are getting carry bit as 1, so you have to consider carry delay. But since at any stage, since there is no carry input, okay, so this particular full adder, third shape full adder, in order to produce 1, it takes 30 nanoseconds. And since there is no carry input here, the last shape full adder, in order to produce this carry output as 1, it is taking 30 nanoseconds only. So that means for all these 4 cases, it requires only 30 nanoseconds. Yes or no? All of you quickly respond. For all these 4 combinations, the moment if you are giving B input, whatever the combination here we have considered, in order to get the valid output, the ripple carry adder is taking only 30 nanoseconds. Yeah, thank you, Nikhil. Thank you. Yes, very good, Savik. Yeah. Now let us see the remaining 4 combinations. 1 plus 1, 2, sum is 0, carry is 1. Here triple 1, that means you will get 1 1. 1 plus 1, sum is 0, carry is 1. Here triple 1 you are having, that means you will get 1 1. 0 1, 1 plus 1, sum is 0, carry is 1. Here 3 ones are there, you will get double 1. 1, 1, 1 plus 1. Sum is 0, carry is 1. Once again, here 3 ones are there. You will get 2 ones. Now, here if you observe, the third stage full adder is producing the carry output as 1. Third stage full adder is producing carry output as 1. Now, because of this, you are getting fourth stage full adder also carry output as 1. Okay. Even, of course, you are getting some output also, you are getting 1. Okay. Either you consider like this. Okay. What is the same example I have considered? Okay. Say, for example, at 0 nanosecond, you are started, 0 nanosecond. This particular carry output, you are getting at 30 nanosecond. You are getting at 30 nanosecond. Okay. Now, after getting this carry only, this particular sum bit will be updated, this particular carry output will be updated. Okay, right. So that means this particular fourth stage full adder has to wait till you are getting this carry input as 1. Once if it is getting, then in order to produce a sum or in order to produce a carry, according to the given question, both the delays are same. So that means once again we have to consider 30 nanosecond. So that means at 60 nanosecond only, you are getting the valid output. Okay, you can consider for all these combinations the same answer you will get. All of you quickly respond whether is it clear or not. The fourth stage full adder, in all these cases, the fourth stage full adder, in order to produce the sum bit or carry bit, it requires 60 nanosecond. It requires 60 nanosecond. Yes, very good, very good. So for all these 4 combinations also, the ripple carry adder is taking 60 nanoseconds. So previously we got 4 combinations. Here we got 4 combinations. Together it is 8 combinations. So the answer for this question is 8. So how many of you liked this question? How many of you felt this is a very, very interesting question? You never seen this type of question anywhere so far. All of you quickly respond. Share your experience about this question. Yes. Okay, this is the typical question. Okay. Now you have learned how to solve this question. Okay, whatever may be the level of the question you may get in your coming GATE exam related to ripple carry adder, definitely you will get. Okay, what are the marks they will assign. Okay, right. So kindly share this video link with all of your friends so that they also will attend this session in live and they also will get benefited, right? So you are getting very interesting questions and which are very much useful for your coming GATE exam, right? So all of you kindly share this video link with all of your friends also. Now the next question is MCQ. That means only one option will be correct. So this question is regarding 4-bit magnitude comparator. So all of you give a try. This is a simple question. Yeah, thank you Savik. Thank you Saptak. Yeah, thank you Vipin. Yeah, thank you, Nikhil. Sure, definitely. Yes, very good, Saptak. Very good. So here they have given 4-bit magnitude comparator. Okay, whenever, see, as the name implies, comparator means it will compare. Okay, and here it will compare only the magnitude. Okay, whenever you are giving two inputs A and B, whenever you are having two inputs A and B, it will give the relation whether A is greater than B or A is less than B or A equal to B, like that. Okay, but here the question is regarding the number of combinations. Okay, see, when you are having 4 bits, yes, very good, Savik, very good. Yes, see, in general, when you are having 4-bit, okay, A is a 4-bit number and B is a 4-bit number. Okay, at the input side, if you write the truth table, regarding A you are having 4 bits, regarding B you are having 4 bits, right? So together you are having 8 bits. That means here at the input side, how many combinations of zeros and ones you will get? Total number of combinations. Since you are having 8 bits, how many combinations of zeros and ones you will get? Total number of combinations of zeros and ones. Not 253, it will be 2 power 8, right? See, if you are having single bit, 2 power 1. 2 bits means 2 square, 4 combination. 3 bits means 2 power 3. In the same way, since you are having 8 bits, total number of combinations are 2 power 8, which is nothing but 256. 256. Yes, very good, Saptak. Very good. Very good, Shavik. Yeah. Total number of combinations you will get 256. Okay, right. Now, here the question is regarding A greater than B. Okay, now I will give different approach. For the timing, let us just tell me, when you are having A is a 4-bit number and similarly B is the 4-bit number. Now consider individually. Okay, say for example, if you are considering A value as all the bits are zeros and B value also all the bits are zeros, then we can say both A and B are equal. Okay, similarly if you are considering 0001 here, 0001 here, then also we can say both are equal. Like that. Now tell me, for how many combinations we will get, both A and B are equal? Number of combinations of zeros and ones related to A equal to B. How many combinations you are having in order to get A and B both are equal? I have discussed 2 combinations. If all the bits are 0 here, also all the bits are 0. That is one combination. Here 0001, 0001. Like that. Yes, very good, Savik. Since you are having 4 bits, you will get 2 power 4 combinations, right? 2 power 4 combinations you will get. Whatever the combination of A you are considering, if the same combination if you are considering for B, then only we will say both A and B are equal, right? So that means here you will get 2 power 4, that is nothing but 16. 2 power 4, which is nothing but 16. So total you are having 256 combinations, out of which only 16 combinations only will give the output as what? Output will say both A and B are equal. Okay, right. So now if you subtract this number from total, okay, if you subtract this number from total, you will get 240. That means 240 combinations are what? A not equal to B. Number of combinations of zeros and ones for A not equal to B. See, if 16 combinations are related to A equal to B, that means the remaining 240 combinations are correspond to what? A not equal to B. So now whatever the number you got, just divide that number with 2. So you are getting 120, right? So 120 combinations of zeros and ones are corresponding for A greater than B. Similarly, other 120 combinations will be for A less than B. Okay, 120 combinations you are having for A greater than B, other 120 combinations you are having for A less than. Okay, here the question is regarding A greater than B only. Even for A less than B also same answer. Okay, related to this model, you follow this approach. First, count the total number of combinations. From there, subtract for equality. How many combinations you are getting? Just subtract this number from total. You will get one number. Just divide that number with 2, because half of the number of combinations you will get for greater relation, other half you will get for less than. Okay, if you are having any doubt regarding this particular method, okay, just verify in your free time with the help of 2 bits or with the help of 3 bits. Okay, just write the tabular form for 2 bits regarding A, 2 bits regarding B, and just observe, okay, for all these cases, so that you will get the clarity. Okay, for the timing I have given direct shortcut. Okay, I haven't discussed any example, but you can try. Here the question is regarding 4-bit, but for easy understanding you can consider A is a 2-bit, B is a 2-bit, and just make the tabular form, and at the input side total you are having 4 bits, and at the output side you just write 3 columns: A greater than B, A less than B, A equal to B, and then you just count. According to this formula also it will match. Okay, here this question is related to 4-bit magnitude comparator. The example that I have discussed is for 2-bit. Okay, so all of you kindly try in your free time. Now the next question, this is MSQ. MSQ, that means either one option or more than one option can be correct. Okay, here they are asking choose the correct options. Either one option or more than one option will be correct. So regarding the output they are asking. Here you are having a 3 to 8 decoder. And in this case, see, sometimes they will give the normal decoder. Normal decoder means outputs they will put direct. Okay, there is no bubbles. But here you are having bubbles. For all the outputs you are having bubbles. Okay, and then here you are having NAND gate. So this overall circuit output, regarding that they have given 4 choices. Option A, what they are saying is this particular output is nothing but sum equation of a full adder. It represents sum equation of a full adder. Option B, they are saying it represents difference equation of a full subtractor. And option C, they have given the equivalent function as product of max terms. And option D, they are saying in terms of number of ones, output equal to 1 if even number of ones are present at the input. So you have to choose the correct option. Here in this decoder, for all the outputs you are having bubbles. Okay, here you are having NAND gate. So all of you try to choose the correct options. All of you give a try. Just recall the concept of decoder, and then NAND gate you are very much familiar. Just try to solve. Yes, very good, Savik, very good, excellent, excellent. See here, you're having 3-tier decoder and output, decoder outputs, instead of direct, they have mentioned the bubbles, and here you're having NAND gate. Here you're having NAND gate. Okay. So whatever the circuit here you're having, I'm just redrawing this one. I'm just considering the NAND gate. Okay. And here you're having 4 inputs. Okay. Instead of direct, you're having bubbles, right? So that bubbles I will represent here. Since in this particular circuit you're having 4 inputs, and for all the 4 inputs you're having bubbles. These bubbles I am just placing here, just for easy understanding. Okay, and here the inputs are what? D1, D2, D4 and D7. D1, D2, D4, D7. Okay, now this is the circuit. Forget about this decoder. Okay, for decoder, normal outputs you are having D1, D2, D4, D7. After that you are having bubbles. Those bubbles I kept here at the input side. Okay, now what will be this circuit? What will be this logic gate? All of you please try. You are having a NAND gate, inputs you are having bubbles. Then that particular logic gate we can replace with which gate? See here, you are having D1 bar, then D2 bar, D4 bar and D7 bar. D1 bar, D2 bar, D4 bar, D7 bar. Okay, these are the 4 inputs you are passing through a NAND gate. So output you will get complement. Inside you are having logical AND. Just apply De Morgan's law. You will get D1 plus D2 plus D4 plus D7. Okay, right. Yes, very good, Saptak. Yes, it's an OR gate. Okay, so this particular logic gate is nothing but OR gate. Previously, we have discussed regarding NOR gate. If the inputs are bubble, there you got AND gate. Here you are having NAND gate, inputs are bubbles. This equivalent circuit is nothing but simply OR gate, right? So in general, now forget about this entire circuit. Okay, now consider the normal decoder. You are having XYZ are the inputs, and now you are having D0 to D7 are the normal outputs. So in general, decoder will produce what? Outputs as minterms, right? So this one you can label as M1 plus M2 plus M4 plus M7. Okay, when you write in terms of the input combination, so these input combinations are nothing but minterms only, right? So you are getting M1, M2, M4, M7, that is nothing but sigma M 1247. Sigma M 1247. Okay, so here they have given pi capital M 0356. 0356. See, when you are having 3 variables, in general you will be having the range as 0 to 7, the corresponding decimal equivalent. Within this range, other than these terms, remaining will be these. Yes or no? Yes, 0 is there, 1, 2 are present there, 3 is present here, 4 is present there, 5, 6 are present here, 7 is there. Correct? So that means option C is correct. Option C is correct. Okay. Now, see, I hope all of you are familiar regarding full adder sum equation. See, for a half adder sum equation is what? A XOR B. For full adder sum equation will be what? A XOR B XOR C. A XOR B XOR C. Or you can write A XOR B XOR C in like that. Okay. Similarly, if you recall, previously also we have mentioned regarding half subtractor, the sum equation regarding half subtractor, difference equation, both are same. Both you got XOR only, right? In the same way, here also for difference equation of full subtractor, you will get the same equation. Generally, you will write like this: A XOR B XOR B in. Okay. Here, according to this question, X, Y, Z are the variables. That means you are having 3 variables. When you substitute here, it will match. See here, you are having 1. Okay. Now tell me, regarding A XOR B XOR C in, the corresponding minterm numbers, you will get this one only. Or if you are having any doubt, all of you please tell me, regarding XOR function, okay, regarding XOR function, whether you will get, for generalized case, whether you will get output as 1 for odd number of ones at the input side or even number of ones at the input side. For which case? For XOR gate, output will be equal to 1. What is the input combination regarding number of ones? Whether is it odd or is it even? Yes, yes, very good. It is for odd number only, right? Very good, Saptak, Savik. Yeah. Now, when you write these 4 numbers in the corresponding binary, okay, 1 is nothing but 0, 0, 1, 2 is nothing but 0, 1, 0, and 4 is nothing but 1, 0, 0, and 7 is nothing but 1, 1, 1. Just observe here, number of ones. Here you are having single one, 3 ones. Number of ones is 1 and number of ones is 3. Okay. So, number of ones is 1 or number of ones is 3. 1 and 3 are odd numbers, right? So, you are having all the 4 possible combinations, right? Regarding number of ones is 1. These are the 3 possibilities. And regarding number of ones 3, this is only 1 possibility when you are having 3 bits or 3 variables, right? So, since you are getting for all the odd number of ones present at the input, okay, for all the combinations of zeros and ones, in which if you are having odd number of ones, you are getting output as 1. So, for odd number of ones present at the input, if you are getting output as 1, that is nothing but the corresponding logic gate is nothing but XOR, right? So, that means here option A, option B both are correct. Option A, option B both are correct. And now, with respect to this understanding, now you can decide here. Here what they have mentioned, for even number of ones present at the input, that time if you want to get output as 1, XNOR gate will produce, not XOR gate, right? So, option D is wrong. So, since this is MSQ, so all the first 3 choices, option A, option B, option C are all are correct. Okay, see here with the help of this question, here you are having the decoder and with the help of some logic gate. Actually, they have given NAND based circuit, but since you are having bubbles, I have just replaced this entire combination with the help of simple OR gate. So, since decoder will produce, sometimes they will give enable, sometimes they won't give. If they give enable, when enable equal to 1, outputs of the decoder are nothing but minterms, right? Generalized case. So, whatever the 4 input combinations you are having, you have to sum together. That means it is a sigma m form. So, that means with the help of decoder and with the help of OR gate, you will get sigma m form. That means sum of minterms form. Okay, right. And here option A, option B regarding full adder, full subtractor. Okay, here we just recalled. Previously we recalled regarding half adder, half subtractor. Now we recalled full adder, full subtractor, right? So, in this way, with the help of decoder and with the help of other logic gate, okay, you can implement any other logic circuit or any other circuit, okay, or any other logic function based on the requirement, right? Now the next question, yeah, now we are going to discuss the questions related to the mux. So this is the MSQ question. That means either one option or more than one option can be correct. They have given a 4x1 mux. You are having the 4 inputs I0 to I3, and here you are having 2 selection lines AB. Here the inputs are C bar 0, 1, C. Here you are having complement. Only for C you are having complement. Starting input C bar, then 0, 1, C. And now regarding output, they have given one choice in sigma m form, one choice in pi capital M, and 2 choices in POS form. So all of you try. So for the time being, whatever you have solved, based on that, which option you are getting correct? Yes, very good. B is correct. B is correct. Yeah, Saptak, you can cross check regarding D. Okay, carefully you can cross check. You are almost closer to the correct answer. Okay, right. So now let us solve this question first conventional method. Whenever you are having mux, okay, for 4/1 mux, the standard equation is f of ABC. Here you are having the output is f of ABC. Okay, see, in general, here for 4/1 mux you are having 2 selection lines and 4 inputs you are having, right? So first I will write the standard equation regarding the output. Y equal to, suppose for a 4/1 mux, the single output for the timing I have assumed y. So you are having 2 selection lines. Okay, if both the selection lines are zeros, 0 0 combination, 0 0 is nothing but what? Equivalent value 0. So that means I0 will be connected. I0 will be connected. Next, for 0 1 combination, for 0 1 combination, I1 0 1 is nothing but 1. So that means I1 will be connected to the output. Next, 1 0 combination, 1 0 is nothing but 2. So I2 will be connected. 1 0 combination, I2 will be connected. And the last combination 1 1, 1 1 is nothing but 3. So I3 will be connected. So this is the standard equation regarding 4/1 mux. Similarly, the similar standard equation you will get with respect to the number of selection lines according to the respective mux. Okay, if you are having single selection line, then if the selection value is 0, I0 will be connected. If the selection value is 1, I1 will be connected. If you are having 3 selection lines, S2, S1, S0, then 8 inputs will be there. So based on the input combination, selection line values here you are having, just convert into the equivalent decimal. That decimal number here you will be having the suffix like that. Okay, just for easy understanding, whatever the decimal equivalent you will get here regarding the selection line combination, that value generally will put here as suffix. Okay, the respective input will be converted to the output. That means at any time, based on the selection values, a particular input will be connected to the output. That's why mux we will call it as switch. Okay, but here you are having the inputs digital form, and this particular, so you can say this particular mux as digital switch like that. Okay, right. Now for this question, here selection lines are nothing but AB, and I0 value is C bar, I1 value is 0, I2 value is 1, I3 value is C. So just substitute all these values in this standard equation. Okay. So f of ABC equal to, here selection lines are AB, so that means A bar, B bar, into I0, I0 value is C bar, then A bar B into I1 value is 0, plus A into B bar, I2 value is 1, plus A into B for last combination, I3 value is C. I3 is nothing but C. Now 0 into anything is 0. Okay, when you are adding 0 to anything, resultant value will remain same. Now you will get A bar, B bar, C bar, plus here you are getting A into B bar plus ABC. ABC. So here they have given one choice in sigma m, one choice in pi capital M, one choice in simplified function. Okay, right. So here if you observe, you are having min term, here also you are having min term. So for the time being, let us convert this one also in the min term form. Okay, so A bar, B bar, C bar I am copying as it is. Here A, B bar you are having. Okay, you can multiply with 1, equivalent value will remain same. That 1 you can write it as C bar plus C, C bar plus C. Okay, so the first term you can copy as it is, A bar, B bar, C bar, then multiply AB bar with these two, A into B bar, C bar plus A, B bar, C plus ABC. Okay, so just place the corresponding values. Here all the variables are complement, that means zeros. Wherever complement is there, just the corresponding variable value will be 0. wherever you're having variable normal form, that means its value will be 1. Its value will be 1. So with this, can you tell the minterm numbers? Sigma m 0, 4, 5, 7. Sigma m 0, 4, 5, 7. Sigma m here 0, 5, 7 is there, so that means it is not correct. Okay, 0, 5, 7 is there, it is not correct. Okay, now let us see whether here you are having 4 max terms, whether it is correct or not, let us see. So here you are getting 0, 4, 5, 7. So that means you can write the corresponding max terms as 1, 2, 3, 6. 1, 2, 3, 6. Yes, 1, 2, 3, 6 only we are having. That means option B is correct. Option B is correct. Okay, so here we eliminated option A and option B is correct. Here the question is MSQ, so we have to verify option C, option D also. If you look at option C and option D, both the choices you are having in the POS form, right? So just now you got pi capital M form. If you do the simplification of pi capital M, after that you will get simplified function in POS form, right? Here variables are ABC. I am considering 3 variable K map. So just place zeros in the respective maximum positions. 0, 1, 2, 3, 4, 5, 6. Okay, so those are the respective, this is the K map correspond to this particular function. Now we have to do the groupings. So you can do the grouping of these 2 zeros, you can do grouping of these 2 zeros. Okay, see, the grouping of these 2 zeros is not required because that is the redundant, right? So that's why in the yesterday class, if you recall, I told that with the experience you will avoid this kind of grouping. But whenever the question is regarding prime implications are essential, that time you will do all the possible groupings. But whenever the question is regarding minimized function, you will do whatever the required groupings. Okay, whatever unnecessary groupings are there, you can avoid. Okay, with the practice, you will come to know that you no need of doing grouping of these 2 zeros. Okay, right. Now regarding this one, A value is 0, that means A plus column wise C value is 1, that means C bar. See, if you are having any doubt, see, in general everyone will do the correct representation for the min terms or the product terms, but sometimes students will do mistake regarding the max terms or the sum terms. Even if you are having any doubt whether what is the notation you have considered, whether it is correct or not, okay, how to verify? Just simple logic. Just substitute A value here 0, C value 1, 0, C value 1, complement of 1 is 0. So that means 0 plus 0 is what? 0. So that means you are getting output as 0 only. So it is correct. So in that way you can cross check. Okay, even if you are having any confusion or if you forget in the exam, just substitute the respective values. For max terms you should get output as 0. For min terms you should get output as 1. Simple. Next, regarding this one, B value is 1, that is B bar, C value is 0, C. So B bar plus C. So here you are getting one sum term, here you are getting another sum term. Since you have taken pi capital M, so whatever the sum terms you got, now we have to multiply. Okay, if you are considering sigma m form, after doing simplification you will get product terms. Those product terms we will sum together, SOP form. Similarly, when you are considering max terms, after doing simplification you will get sum terms, we will multiply them. That is called POS form. So which option is correct? A plus C bar and B bar plus C. So option C is correct. So for this question, 2 choices are correct, option B and option C. Option B and option C. Yes, Saptak. Yeah, that's why I told, even if you do any that kind of silly mistake, just substitute the corresponding input values. So after that, if you are getting the corresponding output, then what is the notation you have assumed, that is correct. Otherwise, just change volta. Simple. In general, you are very much familiar regarding min terms. Regarding min terms, whenever if you are having variable value is 1 means normal form. Variable value is 0 means complement version. Exactly opposite you have to consider for max terms or sum terms. Okay. Right. Now this question first I have solved with the help of conventional method. That means first I have written the standard equation regarding 4/1 max. From there I got regarding sigma m and pi capital M, like that. Okay. Now in order to get sigma m form directly, now I will discuss the shortcut method regarding sigma m form. See here, I hope all of you know that the mux functionality is decided by what? Selection lines. Mux functionality is decided by selection lines, right? So if you are having 4/1 mux, for 4/1 mux, the selection lines are here, S1, S0 are the selection lines. Okay. So just write the truth table of 4/1 mux first. Okay. S1, S0 are the selection lines. Here you are having the output Y. Okay. For 0-0 combination, I0 will be connected. For 0-1 combination, I1 will be connected. For 1-0 combination, I2 will be connected. For 1-1 combination, I3 will be connected. This is the truth table of 4/1 mux. I hope all of you are familiar. Now, regarding this question, we have to represent output in sigma m form. Okay. So first write the variables order as it is. You are having 3 variables A, B, C. Now, according to the given mux, S1, S0 are what? Selection lines. S1, S0 are selection lines. Now, on top of AB, just represent the selection lines S1, S0. According to this circuit, your AB are the selection lines. Okay. Now, with respect to your mux functionality, let us consider one by one. For 0-0 combination, when you have considered selection lines as 0-0, okay, that time I0 will be connected. What is your I0? I0 is C bar. C bar means C value is what? C value is 0. C value is 0. Okay, right. Now, next combination 0-1 case. 0-1 case, I1 will be connected to the output. I1 will be connected to the output, but here I1 value is 0. I1 value is 0. When you are multiplying, see, for easy understanding, you just observe here. See, here I1 value is 0. When you are having I1 value 0, overall term you are getting 0, right? So that means that combination we no need to consider. Okay. Whenever the input is 0, that particular selection and combination you no need to consider. Okay, right. Next, 1-0 case. 1-0 case, I2 will be connected. Here I2 value is 1. I2 value is 1. Okay, in general, what students will do in the exam, they will consider C value 1. Okay, whether is it correct? See here, if you carefully observe, when you are having the input as C bar, that time I have considered C value is 0. C bar means C value is 0, correct? Now, but here you are having constant 1. You are having constant 1. This constant 1 in terms of C, how you can write? You can write C bar plus C. That means you are getting 2 combinations. Regarding 1-0, you are getting 2 combinations. C means C value is 1. That is one combination. C bar means C value is 0. That is another combination. Okay. See, if you are having any doubt, just observe the previous slide. See, here you are having 1. Here you are having 1. That is the constant. Constant 1. That constant 1 I have written as what? C bar plus C. Okay. Here you are having C bar. C bar means C value 0. Just carefully observe. C bar means C value 0. Okay. But here you are having constant 1. That one I have written as C bar plus C. So from there you are getting C value 0, one combination, C value 1, another combination, right? So this is very, very important. In general, students will consider one combination, but you have to consider one more combinations. There is a difference. Okay. See, if you are having any confusion, now you will get the clarity. Regarding the last combination, selection lines 1-1, I3 will be connected to the output. I3 is nothing but what? C. C. C means C value is 1. Now carefully observe. When you are having the input is C, normal form, its value is 1. When you're having the input variable complement form, that means its value is 0. Its value is 0. Now, whenever you're having constant 1, that time you will get two combinations. That time you will get two combinations. Okay. Whenever you're having input as 0, that particular selection and combination you can ignore. Okay. I hope it is clear for everyone. Okay. Now, whenever you're having the truth table, okay, for few combinations you will get output as 1. For remaining combinations you will get output as 0. Now, for these 4 combinations only, you will get this particular output as 1. For these 4 combinations, you will get output as 1. For remaining combinations, you will get output as 0. Okay, so that means these 4 input combinations are nothing but minterms. Is it clear for everyone regarding the shortcut method? How to write directly the minterms? Okay, directly from the given marks. If you are having any doubt, you can ask. 0, 4, 5, 7. 0, 4, 5, 7. We are getting the same thing. This is the conventional approach. This is the shortcut method. Okay, I hope it is clear for everyone. Next question, which is MCQ, that means only one option will be correct. They have given output function as pi capital M. Output function they have given pi capital M. Now they are asking regarding the input combination. Regarding the input combination, they are asking. All of you give a try. This is a very interesting question. All of you give a try. This is a simple question only, but generally students used to do the mistake. Here the choices are like this: C, C bar, 1 0, 1 0 0 1, 0 1, C, C bar, 0 1, C bar, C. See, if you observe the previous question, from the previous question, what is your understanding? Whenever you are having the mux, just by observing the standard equation or after doing the simplification, okay, what you are getting, the function is in which form? Just after substituting the given values, okay, you are getting the output function initially. Either you may get in this, okay, if you do further simplification, you will get one form, or you are getting like this form, correct? So that means the output of mux in general, you will get either SOP form or you may get sigma m form first. After that, if you want to convert, you can convert into pi capital M. That is different. But just by looking at the standard equation, From there you will come to know that either you will get sigma m form or simplified form, like that. Okay, now with this understanding, if you catch that point, okay, now you got the hint. Here they have given pi capital M, so that means you have to convert into sigma m form. Sigma m form. Here 0, 3, 6, 7 is there, so that means 1, 2, 4, 5. So these are the min terms. Okay, since you are having 3 variables, for these 4 combinations you are getting max term, that means remaining 4 combinations 0, 1, 2, 3, 4, 5, 6, 7, right? Okay, now if you observe the previous question, for the mux they have given the input variables, they have given the input values also in terms of the variables or in terms of the constant. From there we got the output function in terms of sigma m form. This is one variety of question regarding mux. Okay, another variety is they have given already sigma m form, they have given the selection lines. Now they are asking what are the input values. Okay, one approach is they have given the inputs, they have given the selection lines, they are asking the output form. Okay, and in another cases they are given the selection lines, they are given the output function. Now they are asking what are the inputs. Okay, right. I hope up to this point it is clear for everyone. If you are having any doubt, you can mention in the chart, I will clarify. So this is a very, very important conclusion point. That's why I have discussed earlier question in conventional approach first and then shortcut method. Okay, right. Now once if you get this one, here the variables are what? ABC. So just write the variables order as it is. Now regarding these 4 combinations, write the equivalent binary. 1 is nothing but 0, 0, 1, 2 is nothing but 0, 1, 0, and 4 is nothing but 1, 0, 0, and 5 is nothing but 1, 0, 1. Okay, just write the equivalent binary. Now according to this circuit, the selection lines are AB. So on top of AB, just put the selection lines S1, S0 you can put. Now just make the partition like this. Why I am partitioning like this? Because with respect to mux functionality, selection lines are S1, S0. Okay, so just now I have shown the truth table of mux. Regarding mux, this is the truth table. Now we are following the same. According to the truth table, we are writing the corresponding, we are determining the inputs. Okay, so for 0, 0 case, I0 will be converted to the output. Now here, since C value is 1, that means I0 value is C. Okay, if you are having any doubt, just observe the previous slide. See, when you are having here C, that means I have written C value 1. Okay, if you are having C value 1, that means the corresponding representation is C. Okay, right. Next, for 0, 1 combination, 0, 1 is nothing but 1. So I1 will be converted to the output. So here C value is 0, that means C bar. C value 0 means C bar. Next, for 1, 0 combination, you are getting 2 cases. For 1, 0 combination is nothing but I2 will be connected. Here C value 0 means C bar plus C value 1 means C. C bar plus C is nothing but 1. Now for 1, 1 case we are not getting, that means I3 value is 0. See, for easy understanding, just observe the previous slide. When you are having input as C, that means its value is 1. If you are having C bar, means C value is 0. Okay, if you are having constant 1, you are getting two values for C. If you are having input as 0, that particular selection line combination we are not at all considering, right? So with this understanding, I0, I1, I2, I3 we got like this. Now how many of you say option A is correct? All of you please respond quickly. How many of you say option A is correct? See, most of the times in hurry, most of the students, okay, the moment you got I0, I1, I2, I3 like this, so here also you are having C bar 1, 0. Okay, so because of that, most of the students will choose option A as correct. But see, option A will be correct if they have asked I0 to I3. I0, I1, I2, I3. But here what they have asked, I3, I2, I1, I0. That means you have to consider reverse. Okay. So just observe this one. 0, 1, C bar C. Yes, this is correct. Okay. So according to the order, you have to mention your answer. Okay. Yes. Okay. Right. If they ask I0 to I3, then option A is correct. Since they have asked I3 to I0, option D is correct. Okay. According to the notation, you have to give your answer. This is very, very important. Now the last question regarding this chapter. This is the MCQ question. Only one option will be correct. So here they have given two muxes. Both are 2 by 1 mux only. Here you are having selection line is A. Here selection line is C. Here I0 is B bar, I1 is B. I0 is output of this NOT gate, I1 is output of this mux direct. So they are asking the final output expression. Final output expression F they are asking. Regarding that, they have given 4 choices. You have to choose the correct one. Yeah, thank you, Amit. Yes. See, in general, you might be very much comfortable while you are learning the concepts. You might feel that we know all the concepts very well. But most of the time, in general, students will face the difficulty while you are solving the question, right? So, even though this is the easy subject, but if you take negligence, okay, that means if you not read the question carefully, then definitely, even though you know the concept, but you may choose the wrong answer, right? So later what will happen? Because of that you will get negative marking. Later you will feel regret, right? So that's why try to avoid all these kind of silly mistakes. Okay, even though you know the subject very well, but still read the question carefully. There will be one important keyword in the question. So based on that keyword, accordingly you should give the answer. Okay, so that is very, very important. Yes, very good, Saptak, very good. Others also please try. This is the last question regarding this chapter. Okay, see here they have given 2 by 1 mux. They have given 2 by 1 mux. For 2 by 1 mux, the standard equation is S bar I naught plus S into I1. S bar I naught plus S into I1. Okay, so for the time being, output of first mux I am assuming as say F1. F1. So here selection line is A, that means A bar. A bar. Next, here selection line is A. Now here I0 is B bar, I0 is B bar, here I1 is B, I1 is B. So that means A bar B bar plus AB is nothing but what? AX nor B, AX nor B. Okay, see here one more important point. In general, they will mention like this, I0, I1 in the same order, but sometimes they will do twist. Just observe here, I0 is present here, I1 is present here. But here I0 they have given down, I1 at top. Okay, so with respect to mux functionality, whenever selection is 0, I0 will be connected. Selection 1 means I1 will be connected. Whatever the order they might have represented. Okay, be careful with respect to the notation. Now, regarding output of second mux, F equal to, here selection line is C, so that means C bar into I0. I0 is nothing but F1 bar. Here F1 is input, output of NOT gate is F1 bar. Then selection line is C, input is I1, I1 is nothing but F1. So just substitute your F1 here. So here C bar into F1, F1 is nothing but A XNOR B. You are having complement plus C into F1 is nothing but A XNOR B. Now complement of XNOR is nothing but XOR. Then A XNOR B you can write as complement of XOR. Now just observe, like X bar Y plus XY bar is nothing but what? X exclusive or Y, where X is nothing but A XOR B and Y is nothing but C. So this one we can write as A XOR B XOR C. Okay, in the last class also we have discussed regarding this particular kind of expression, right? Yes. So the correct answer for this question is option C, A XOR B XOR C. Okay, so last two questions I hope all of you liked, because there is a twist, right? In the previous question they asked I3 to I0. In this question they have given I0 I1 order like this, I0 I1 order ulta they have given, right? Yes, very good, very good. So with this we have completed the questions related to chapter 4. So here we have discussed the questions based on half adder, half subtractor, full adder, full subtractor, and then ripple carry adder, magnitude comparator, decoder, multiplexer. Okay, all the possible combinations and all the important models with respect to your coming GATE exam we have covered regarding third chapter and fourth chapter of digital circuit subject, right? So tomorrow we are having one more session. Okay, so please attend that session also. Okay, in that session we will discuss the remaining three chapters, chapter 5 sequential circuits, and then data converters, and then CMOS logic family. Okay, so before leaving the session, so I will give some brief overview about our courses. Okay, some of the students are asking what are the programs are offered by the IMS GATE Academy. So for that I am sharing some information. Yeah, thank you Saptak, thank you. So here when you click on imsindia.com, you will get the various courses offered here. Okay, just click on GATE. Okay, then after that you will get you can select the respective branch, EC, electrical, instrumentation, computer science, mechanical, civil, etc. Okay, so here in IMS GATE Academy we are having various programs like classroom program, and then hybrid classroom, then exclusive live online, and then self-learning program. These are the 4 programs available. So regarding classroom program, we are having 750 plus hours offline classes. That means all the classes are in offline mode only, and you are having 22 to 30 books, which includes theory books, exercise books. So you are having 4000 plus practice questions. Here you will be having level 1, level 2, level 3 questions. Okay, so that while you are solving these questions, you will get the good command over the concepts. And then you will get GATE question bank, previous questions. You are having access of doubt solving portal, and then my plan sessions, and you are having test series, chapter test, subject test, multiple subject test, full length test, and you are having 130 plus various test series together, all together 130 plus. And then you are having post GATE guidance. And in hybrid classroom, you are having same number of hours, 750 plus, out of which 2/3 will go in the offline mode and 1/3 will go in the online mode. Remaining features will be same. Here you are having the access of GATE online live access, and remaining features will remain same. And exclusively live online program, here all the classes will be online only. Okay, remaining all features will remain same. Then regarding self-learning program, here you will get the access of 400 plus hours recorded video lectures. Okay, and then you are having the access of theory books, exercise books, doubt solving portal, etc. And here in our IMS GATE Academy, we will follow this approach, LPT, learn, practice and test. See, For learning purpose, you're having the access of attending our classes either offline or online mode, and you're having the theory books, and you're having the solved examples you can solve from exercise book, etc. So for practicing questions, you're having exercise books, and then GATE question bank you will be having. Okay, by solving these questions, you will get the good command over the subject. And after learning, after doing these two stages, if you are attempting the tests, from there you will get the real, okay, confidence. Okay, how much, in which concepts you are very much comfortable, in which concepts you need to improve further, etc. You will come to know while you are applying the tests. So these are the various tests we are having. So regarding this, we already discussed. Okay, so total we are having 130 plus tests. So the one of the most important here, so IMS GATE Academy is providing GATE at zero fee. Okay, when you click on our website imsindia.com, okay, after that, when you, here you're having branches, first select the GATE mechanical, after that you can select the respective branch. Okay, when you click on that, you will get on this particular web page, you will get this particular zero fee program features. Okay, so here when you enroll here, all these you will get for just for free of cost. Okay, you don't need to pay even single rupee. Here you will get the access of 100 plus hours of concept video and 12 chapter tests, 6 subject tests, 6 previous GATE papers. Okay, you will get the access of all these. Okay, you don't need to pay even single rupee. Okay, and then regarding our students will get the access of our portal. Okay, and then here you are having the access of doubt solving. See, this is one of the most important feature which we are having. See, in general, when you are attending the classes, what are the doubts you are having, you can ask the faculty. But while you are practicing the questions, either from exercise book or from the GATE question bank, okay, from any source, while you are solving the question, if you are getting any doubt, instantly you can post your query by selecting your respective subject, and then whatever the screenshot of the question you are having, you can just upload here. Within 24 hours, our faculty team will resolve your query. Okay, and then this is one of the most important feature IMS GATE Academy is providing, that is My Plan session. Okay, no institute in India is providing this kind of feature. Okay, in general, if students are having any doubts, if the students want to have one-to-one interaction with the faculties, they can book the slot, they can discuss, they can get the guidance from the corresponding faculty. Here we are having the feature of one-to-one and one-to-many also. Yeah, this is all about regarding our programs. So even though you are preparing for 2023, okay, if you are targeting for 2023 also, you can have the access of zero fee program, and even the students who are preparing for 2024, they also can register for a zero fee program. Okay, so that whatever our products we are having regarding video lectures, books, etc., all of you can have a glance and you can get benefited from that. Okay, right. So all of you please share your experience in the chat regarding today's lecture. In today's session, we have discussed the questions related to logic gates and combination circuits. All of you kindly share your experience. What is your confidence level after attending today's session? All of you please share your experience in the chat. Yes, very good, very good. Yeah, all of you got the confidence regarding logic gates and combination circuits, right? So tomorrow we are having the next session regarding digital circuits, that is part 3. Okay, so in tomorrow's session we will discuss the questions related to sequential, then data converters, then CMOS logic family. For CS branch, the up to sequential is the common syllabus. Okay, whereas for other branches, we regarding electrical instrumentation, you'll be having data converters, logic family, like that. Okay, so you can attend whatever may be the branch you may belong to, you can attend the complete session, because Even though we are discussing data converter question, still we will use the concept of first chapter, even logic family also, so that you can attend our session tomorrow thoroughly, whatever the branch you belong to. But later when you are preparing, CS students can skip the last 3 chapters, okay, whereas electrical students can skip the last 1 chapter, like that, okay. CS students up to 5th chapter, electrical students up to 6th chapter, whereas ECIN up to 7th chapter, okay. I hope all of you learned a lot from this session, okay. So we'll meet you all on tomorrow's session at 6 p.m. sharply, okay. Thank you all. Good night. Take care. Bye bye.